Hello there, and welcome to Physics with William, where curiosity settles in, the noise of the day eases back a little, and science is allowed to unfold at a gentler pace. Tonight, we are turning our attention to something very small, very familiar, and yet surprisingly easy to overlook. We're going to spend some time with a particle that quietly shapes almost everything around you. From the screen you may be listening beside, to the atoms in your hands, to the electrical activity moving through your own body at this very moment. The subject is the lepton, and more specifically the hidden particle identity tucked behind the electron, that modest little resident of the atom that most of us first met in school and then politely stopped asking too many questions about. And that is rather understandable, really. The electron has a reputation for being one of those things everyone has heard of, but not many people are invited to sit with for very long. It appears in diagrams, in textbooks, in science class demonstrations involving balloons and static cling, and perhaps one unlucky hairstyle. It gets introduced as a tiny negatively charged particle that buzzes around the nucleus of an atom, and for a while, that feels perfectly satisfactory. Case closed. The world moves on. But physics, as it so often does, has a habit of taking the apparently simple and opening it like a box with far too many compartments. Because the electron is not just an electron in the casual schoolroom sense, it belongs to a deeper family. It follows rules that are far stranger and more exact than the cartoon picture usually suggests. It is one member of a set of particles that physicists group together under a name that, at first hearing, sounds almost unreasonably elegant for something so technical. Lepton, a quiet word, a lean word, one that does not immediately announce the scale of the ideas attached to it. Before we get too far into that, though, let me ask you something simple. Where are you listening from tonight? Are you at home under a blanket, in a dim room with the day nearly finished, or perhaps on a train, or in bed with the screen turned low, trying to let your thoughts settle without giving them quite enough material to run wild? And while you are there, what time is it in your little corner of the world right now? There is something fitting about that question whenever we talk about physics. These ideas may belong to the whole universe, but every listener arrives at them from one very specific place, at one very ordinary human hour. If you find this kind of slow scientific wandering soothing or interesting, or simply a pleasant way to wind down while your brain decides whether it still wants to be productive or would rather become a loaf of bread for the evening, I would be very grateful if you liked the video and subscribed. It helps this quiet corner of science reach people who might need a calmer kind of explanation. And now, with that gentle bit of housekeeping out of the way, let us ease into the matter at hand. If I say the word particle, there is a fair chance your mind produces a familiar set of images. Tiny things, building blocks, perhaps little balls, very small, very energetic, bouncing about in ways that become gradually more alarming the longer a physicist talks. That instinct is natural, but as usual with the smallest ingredients of reality, the truth is less tidy than the picture. Even so, the picture can still be useful if we handle it carefully. Imagine for a moment that you're looking at the world not as a collection of chairs, windows, raindrops, skin, copper wire, or coffee cups, but as layers of structure. Big things made of smaller things, which are made of smaller things again. For a long time, the atom seemed like a sensible stopping point. The word itself came from the old idea of something indivisible, something that could not be cut any further. That confidence did not survive contact with modern physics. Atoms turned out to have internal structure, a nucleus in the middle, electrons associated with it. Then the nucleus itself turned out not to be final either. Protons and neutrons were made of quarks, and somewhere in this increasingly crowded story, the electron remained oddly stubborn. It did not seem to break apart. It did not reveal smaller pieces tucked inside it. It just kept showing up as itself. That matters more than it first appears to. In particle physics, one of the first important distinctions is between things that seem composite and things that seem fundamental. Composite means built from smaller ingredients. Fundamental means, as far as we can currently tell, not built from smaller ingredients at all. The proton is composite, the electron appears fundamental. And the lepton is the category into which the electron falls. Now, if the word category makes this sound a bit like a filing cabinet, that is not entirely wrong. Physicists do a great deal of sorting. Nature, after all, presents us with a bewildering number of behaviours, interactions, patterns and entities, and one of the first tasks of science is learning what belongs with what. Some particles clump together under the strong nuclear force, some do not. Some carry one type of charge, some carry another, some have mass, some appear not to. Some are stable enough to hang around in ordinary matter. Others vanish so quickly that describing them almost feels rude, as though we are introducing someone at a party just as they are already leaving through the garden. Leptons are one of the major families in this sorting effort. The electron is the most famous of them because it is everywhere in ordinary life. It participates in chemistry. It determines the structure of atoms beyond the bare nucleus. It is central to electricity, bonding, magnetism, and the practical reality of electronics, which is a little amusing when you think about it. Entire civilizations now depend on the disciplined motion of an invisible particle that most people have never once pictured correctly. But calling the electron a lepton means something more precise than simply saying it is important or small. It places the electron among particles with a particular kind of identity. Particles that do not participate in the strong nuclear force. Particles that seem, in our current best understanding, to be fundamental. Particles that come in a family that includes not only the electron, but also the muon, the tau, and their corresponding neutrinos. If those names sound a bit like a mix of Greek letters, science fiction side characters, and someone losing a game of Scrabble, do not worry. They will become much more sensible once we spend time with them, or at least more familiar, which in physics is often the next best thing. It helps, at the beginning, to notice just how misleading familiarity can be. The electron feels familiar because we hear about it early. That can trick us into thinking it is simple. It is not simple. It is merely familiar in the same way your own name is familiar. You may hear it every day, but that does not mean it contains no mystery. The electron has charge. It has mass. It has a property called spin, though not in the everyday sense of a spinning object. It behaves according to quantum rules that do not line up with ordinary intuition. It cannot simply sit wherever it likes in an atom. It occupies allowed states. It contributes to the shape and behaviour of matter in ways that are exact, constrained, and deeply strange once you stop to think about them. And yet, even all that is only part of the reason the lepton matters. The deeper reason is that the lepton helps reveal the structure of the particle world. It tells us that the electron is not an isolated oddity. It has relatives. It belongs to a pattern. And in physics, patterns are rarely accidental. When nature repeats herself with variation, scientists become very attentive. Sometimes that repetition points to a hidden rule. Sometimes it points to an unfinished theory. Sometimes it points to a deeper simplicity concealed beneath a mess of observations. And sometimes it points to the universe being, frankly, far stranger than anyone ordered. One of the oddest things about modern particle physics is that it often advances by discovering not just what exists, but how many versions of something exist, why one family is repeated, why the same basic type appears in heavier forms, why some particles are stable enough to fill the world around us, while others seem to show up only briefly in energetic environments, like guests who are technically invited but clearly not planning to stay for the tea. The Lepton family has exactly this sort of puzzling structure. The electron is the one we know best, but it is accompanied by the muon and the tau, which behave in many ways like heavier cousins, as well as by neutrinos, which are elusive enough to make almost any other particle look socially available by comparison. So when we ask what a lepton really is, we are not asking for a dictionary entry. We are asking a more useful question. What kind of thing is the electron truly, once we stop treating it as a textbook prop? and begin placing it in the actual framework of fundamental physics. What does it mean that it belongs to this family? What rules define that family? Why should matter include such particles at all? And why does one of them, the electron, end up sitting so quietly at the centre of everyday reality, while its relatives remain mostly invisible to ordinary experience? These are the sorts of questions that make particle physics feel different from the science many people meet in school. School science often gives the finished outline. Here is the atom, here is the nucleus, here are electrons, here is how current works. Useful, practical, manageable. But once you continue beyond that first introduction, the neat outline starts to blur into a deeper landscape where the categories become more important than the pictures. You begin to care not just that something exists, but what sort of existence it has, whether it is fundamental or composite, what interactions it participates in, what symmetries define it, what family it belongs to. And suddenly a common word like electron becomes less like the end of an explanation and more like the beginning of one. There is also something quietly humbling about the fact that one of the central particles in daily life is hidden in plain sight by its own normality. We do not notice electrons because they are not unusual to us. They are woven into everything too thoroughly to stand out. The spectacular tends to grab more attention in physics. Black holes, antimatter, exploding stars, quantum paradoxes, perhaps the occasional headline suggesting that reality is not locally real, which is the sort of phrase that can do alarming things to a relaxed evening. But the electron is different. It is not flashy. It is dependable. It is part of every atom of ordinary matter except the simplest bare nuclei. It helps make chemistry possible. It helps define the surfaces of objects. It helps determine why your hand does not pass through the table. That last point is especially worth appreciating, because there is nothing like a quiet evening and a sturdy table to remind us that invisible particles have standards. Still, even here we should be careful. Saying the electron is a particle does not mean it behaves like a tiny grain of dust tucked inside matter. In the quantum world, the language of particles remains useful, but only if we remember that it is attached to behaviour far stranger than the word suggests. An electron can be localized in some circumstances and wave-like in others. It can interfere. It can be described by a quantum field. In modern theory, the electron is not best imagined as a hard little bead bouncing through miniature solar systems. That old image persists because it is easy to draw, not because it is especially accurate. And perhaps that is part of what makes the Lepton such a good subject for a slow beginning. It asks us to unlearn gently, to set aside the first simplified picture without becoming lost in abstraction, to accept that the electron is both more ordinary and more mysterious than we thought. More ordinary because it belongs to a family rather than standing alone. More mysterious because that family itself opens onto questions about why the universe has the inventory it does. If you were to zoom in, not with a microscope, because microscopes ceased to be the right tool long before this point, but with the conceptual machinery of high-energy physics, the world would begin to reorganize itself before your eyes. Tables and skin and water and stone would no longer look like continuous stuff. They would begin to resolve into structured systems of atoms. Those atoms would resolve into nuclei and electrons. The nuclei would resolve into quarks bound together, and there the branching begins. The quarks belong to one family, the electron belongs to another. Already the world is no longer made of one kind of fundamental thing, but several kinds with distinct roles. That is one reason particle physics can feel both elegant and slightly overstaffed. There is a pattern to it, yes, but there is also a caste list. Quarks, leptons, force carriers, the Higgs, each with properties, generations, interactions and behaviour that fit together in a model of remarkable predictive success, and yet still leave enormous questions unanswered. The standard model, which is the name given to this framework, is not standard in the everyday sense of dull or generic. It is standard in the sense that it is the established theory currently used to describe the known fundamental particles and their interactions aside from gravity. An unfortunate bit of naming, perhaps. One can imagine generations of students hearing the phrase and expecting something plain, only to discover instead a highly precise catalogue of reality involving particles that appear and vanish, fields that fill space, and a neutrino population so abundant and elusive that it borders on rude. Within that model, leptons occupy an important place. They are not side characters. They are part of the main architecture. But because the electron is the only lepton that strongly shapes our visible and tactile daily world in such an obvious way, the entire family can remain somewhat hidden from public imagination. Ask someone what matter is made of and they may mention atoms. Ask them what atoms contain, and they may mention protons, neutrons, and electrons. Ask which category the electron belongs to, and the conversation may suddenly become much quieter. That quiet is where we begin. Because one of the pleasures of physics, especially at this slower pace, is noticing where familiar words conceal unfamiliar depth. Electron is one such word. Lepton is another. Together they mark a shift from the science of surfaces to the science of classification and identity. And identity matters here. Not identity in the human sense, of course, though particles are surprisingly fussy about who they are allowed to be. Identity in the sense of fundamental properties, what interactions a particle participates in, what mass it has, what charge it carries, whether it is stable, whether it belongs to a repeated family pattern, whether it builds the world directly or visits it briefly under special conditions. As we move further into this subject, we will need to do something that physics often demands. We will need to resist the temptation to ask only what a thing looks like, and instead ask what it does, what rules it follows, and what category of existence it occupies. This is not always intuitive. Human beings are visual creatures. We like pictures. We like little orbiting electrons and tidy atomic diagrams because they feel graspable. But the deeper truth is usually written in behaviour. The electron counts as a lepton not because of how we draw it, but because of how it fits into the pattern of nature. That pattern is not merely an academic curiosity. It is the reason the world has the form it does. If electrons were different, chemistry would be different. If leptons interacted through the strong force the way quarks do, matter would not organise itself as it does now. If the electron were unstable in the way heavier relatives are unstable, ordinary atoms might not persist. The entire calm reliability of daily material existence depends in part on the exact identity of this one quiet lepton. A remarkable amount of normal life rests on an invisible particle getting its properties exactly right. And so tonight, rather than rushing to definitions as though we were trying to catch the last train home, we're going to let the question settle properly. What is a lepton really? What sort of particle is the electron once we understand that it is part of a family and not an isolated object? Why does that family exist? What makes leptons different from quarks? Why do some of them fill the universe around us while others hide in high-energy events and in the thin streams of particles passing unnoticed through your body even now? Those questions take a little patience, but they reward it. For now, it is enough to notice that the electron is not just the atom's outer resident, not just the keeper of chemical bonds and electric current, not just the schoolbook negative charge bobbing somewhere in memory. It is a lepton. That single reclassification quietly changes the scale of the conversation. It takes us from the atom to the standard model, from chemistry to fundamental physics, from the familiar edge of matter into the deeper catalogue of what the universe appears to be made from. And once that shift happens, the ordinary electron begins to look less like a simple particle, and more like the first visible clue in a much larger family story, one that starts with the one we think we know best, and then asks whether we have ever really met it properly at all. Now, when most people first meet the electron, the introduction is almost suspiciously tidy. It arrives in school as a small, negatively charged particle associated with the atom. Usually it is shown as something that sits around the nucleus, perhaps circling it in neat paths, looking for all the world like a tiny planet in a very committed solar system. It is the part of the atom that explains electricity, chemical bonding, static shocks, and the occasional unfortunate encounter between a wool sweater and human hair. This is useful as a first meeting. It is not useless. But it does leave the impression that the electron is a settled matter, a piece already filed away, understood well enough to stop worrying about. Physics, unfortunately for our desire to feel finished, is not especially fond of settled matters. The electron is one of the best known particles in science, and also one of the easiest to underestimate. It is familiar in the way that air is familiar. It is everywhere, so thoroughly woven into ordinary life that we stop noticing how strange it really is. Every solid object you touch owes much of its behaviour to electrons. The chemistry of life depends on them. The light from your screen, the current in a wire, the structure of a molecule, the shape of an atom beyond its bare nucleus. All of it is tied to this small and elusive constituent of nature. If the proton helps anchor matter at the centre of the atom, the electron is what gives matter most of its texture, most of its reactivity, and much of the visible drama of the everyday world, and yet it is not visible at all. No one has ever peered into an atom and watched a little bead-like electron doing laps around the nucleus, as if training for some microscopic marathon. That picture persists because it is easy to draw and easy to teach. The real electron is harder to hold in the mind. It is not a tiny marble, it is not a grain of dust, it is not a miniature planet, it is a quantum object, and that phrase, though often repeated, conceals an enormous amount of mischief. Before we get to the strangeness, though, it is worth noticing something more basic. The electron was the first subatomic particle to be discovered. That alone gives it a special place in the history of physics. There was a time when atoms were thought to be the smallest pieces of matter, the final bits at the bottom of the stack. Then, near the end of the 19th century, experiments with electric currents in glass tubes began to suggest that something smaller was at work. Cathode ray tubes, which sound rather elegant until you picture a workshop full of glowing glass apparatus and scientists leaning in with expressions of concentrated confusion, produced mysterious streams that could be bent by electric and magnetic fields. That bending mattered. It meant the rays were not simply some ghostly kind of light. They were made of entities carrying charge. The physicist Joseph John Thomson studied these rays and came to a remarkable conclusion. They consisted of particles much smaller than atoms. This was a serious disturbance to the old picture of matter. If atoms had pieces, then atoms were not indivisible after all. The supposed final brick had internal structure. Thomson had found the electron, though the word itself settled into use gradually, and with that discovery the atoms ceased to be the end of the story. There is something charming about how often science advances by ruining a perfectly good simplification. At first, the electron was defined by what it seemed to do. It carried negative electric charge. It had a very small mass compared with atoms. It could move through materials and under the right conditions leap between them. It was involved in electricity. Those were powerful clues, but they did not yet add up to the rich identity the electron would later acquire. In the early days of atomic theory, scientists were still figuring out how these newly discovered particles fit into the atom at all. Thomson himself imagined the atom as a kind of positively charged pudding, with electrons embedded inside it like fruit. This image has never fully recovered its dignity, but it was at least an honest attempt to account for the facts available at the time. Later experiments, especially those associated with Ernest Rutherford, showed that the atom had a small dense nucleus with electrons outside it. That was closer to the truth, but even then the electron remained puzzling. According to ordinary classical physics, a charged particle moving in a curved path should radiate energy. An orbiting electron ought to lose energy, spiral inward, and collapse into the nucleus. Atoms should not be stable. Matter should not sit around minding its own business for billions of years. The fact that it does meant the old picture was wrong, or at least badly incomplete. And here the electron helped force one of the greatest changes in scientific thought. To understand atoms, physicists had to leave behind classical intuitions and enter the quantum world. They had to stop treating the electron like a tiny object moving along a little track and begin treating it as something governed by probabilities, allowed states, and wave behavior. The electron was not just a new particle. It was one of the main reasons reality had to be described in a new language. That shift is worth lingering over because it marks the point where the electron begins to reveal its true depth. In ordinary speech, to know something often means to picture it clearly. We know a chair because we can see it. We know a spoon because we have held it. But in quantum physics, understanding often means giving up the demand for an easy mental picture and learning instead to trust the structure of the theory. The electron does not offer itself to common sense in a generous spirit. It behaves in ways that are exact and measurable, but not especially comfortable. For one thing, the electron has a fixed amount of electric charge. Not approximately, not on average, but exactly. Every electron everywhere carries the same negative charge. This sameness is one of the quiet marvels of particle physics. Electrons in your body, electrons in a copper wire, electrons in a distant star, electrons produced in a laboratory, all are indistinguishable in their fundamental properties. They are not siblings with slight differences. They are identical in a much stricter sense than ordinary objects ever are. There is no slightly taller electron or unusually thoughtful one. Nature does not personalize them. It mass-produces perfection with unnerving consistency. The same is true of the electron mass. Every electron has the same mass as every other electron. That mass is tiny by everyday standards, though everyday standards are not especially useful down here. Compared with protons and neutrons, the electron is much lighter. That fact has profound consequences. Because electrons are so light, they respond readily to forces. Because they carry charge, they are central to electromagnetism. And because they are quantum objects, they occupy atoms in ways that determine the structure of chemistry. This is where the electron begins to step out of the background and become the real architect of ordinary matter. The nucleus may contain most of the atom mass, but the electrons define the atom's size and behavior. Chemical bonds are about electrons. The difference between one element calmly ignoring another and eagerly reacting with it is largely a matter of electron arrangement. Why oxygen binds the way it does, why carbon can build elaborate molecular frameworks, why metals conduct electricity, why some materials are brittle and others flexible, why life chemistry works at all. All of these questions pass through the electron on their way to an answer. If protons and neutrons are the heavy furniture of atomic structure, electrons are the interior design, the wiring, the doors, the windows, and much of the atmosphere. Even our sense of touch depends in part on electrons. When you press your hand against a table, you're not really making contact in the everyday sense of little bits physically merging. The electrons in the atoms of your skin and the electrons in the atoms of the table resist occupying the same states in the same way. Electromagnetic interactions and quantum rules keep matter from simply passing through matter. So the apparent solidity of the world, that dependable refusal of chairs, walls and floors to let us drift through them like perplexed ghosts, owes a great deal to electron behavior. It is one of the lovelier facts in physics that the stubborn practicality of furniture rests on something so invisible and so conceptually strange. And conceptually strange it certainly is. The electron does not have a sharply defined little path inside an atom the way planets move around the sun. Instead, quantum theory describes allowed states. These are sometimes visualized as clouds of probability, regions where the electron may be found if measured. This is already very different from the schoolbook orbit picture. The electron is not wandering in a random fog, but neither is it tracing a neat ring. Its behavior is constrained, quantized, and described by patterns that tell us where it is likely to be found and how it can change state. Now, the The word likely can make this sound as though physics has become vague or indecisive. Quite the opposite. Quantum mechanics is extraordinarily precise. What it gives up is not rigour but certainty of the classical kind. It tells us what can be said and what cannot. It tells us how outcomes are distributed. It tells us the allowed structures of atomic behaviour with astonishing success. The electron obeys those rules whether or not they feel satisfying to our old intuitions. There is another layer to this that makes the electron even more interesting. It is not only a carrier of charge and a participant in chemistry, it also has an intrinsic property known as spin. This is one of those terms in physics that would have benefited from a more cautious naming committee. Spin does not mean the electron is literally a tiny rotating ball. If it were, the classical picture would lead to all sorts of impossible consequences. Spin is instead a built-in quantum property, a form of angular character that affects how electrons behave in magnetic fields and how they can share quantum states. This matters tremendously for the structure of matter. Electrons belong to a class of particles that obey the Pauli exclusion principle. In plain language, electrons are extremely unwilling to pile into the exact same quantum state under the same conditions. This is not a matter of temperament, though it does sometimes sound like one. It is a basic rule of quantum behaviour for particles of this kind. Because of it, electrons stack themselves into different atomic states rather than all collapsing into the lowest one. This gives atoms their layered structure. It gives the periodic table its shape. It gives chemistry its richness. Without this refusal of electrons to all become identical occupants of a single state within an atom, the ordinary complexity of matter would vanish. So the electron is already doing rather a lot. It is discovered as a small charged constituent of matter. It forces the atom to be reconsidered. It helps drive the birth of quantum theory. It shapes chemistry. It governs electricity. It contributes to the solidity of objects. It obeys exclusion rules that make the complexity of matter possible. This is not a minor supporting role. It is one of the central jobs in the entire physical drama. And still the electron has another surprise waiting, because even after all that, it is not just itself. It belongs to a family. This is where our familiar particle begins to change identity in a subtle way. Once physicists built a more complete map of fundamental particles, it became clear that the electron was part of a broader category called leptons. That means the electron is not a lone curiosity but a member of a pattern. It has relatives. Some of those relatives resemble it closely but are heavier and unstable. Others are neutral and astonishingly elusive. The moment you place the electron in that family, its meaning changes. It is no longer simply the electron, the familiar charge carrier of atoms. It becomes one example of a deeper particle type. But before we move too quickly toward those relatives, it is worth staying with the electron just a little longer, because the deeper one looks, the more impressive its stability becomes. The electron appears to be stable. It does not decay in any observed everyday sense. Other particles transform. Neutrons outside nuclei decay. Muons decay. Taus decay. Many heavier particles are so short-lived that describing them almost feels like trying to introduce someone while they are already halfway out the door. The electron remains. That stability is essential to the world we know. If electrons routinely decayed away, atoms would not keep their structure. Chemistry would become a very different affair, and life, if possible at all, would be something we would no longer recognize. This stability gives the electron a peculiar combination of modesty and authority. It is light, but not massless. It is small, but not negligible. It is invisible, but constantly at work. It is deeply quantum, but responsible for many of the most ordinary features of matter. It is one of the simplest known particles and one of the most consequential. Familiarity, in this case, has been hiding importance in plain sight. Even the way electrons move through materials is more subtle than the simple picture of tiny balls rolling down wires. In metals, for example, electrons occupy collective states influenced by the structure of the material. Their behaviour is described not only by individual motion, but by quantum statistics and the architecture of the solid itself. In semiconductors, the controlled behaviour of electrons underlies all modern electronics. Computers, phones, sensors, memory devices, the entire delicate empire of digital civilization rests on our growing ability to persuade electrons to move, pause, tunnel, and reorganize themselves in precisely engineered materials. One cannot help feeling that the electron, had it any opinion on the matter, might be a little annoyed that after all this service it is still mostly represented to the public by a few circles around a nucleus in an old textbook diagram. Then there is the electron in light and radiation. When electrons change states in atoms, light can be emitted or absorbed. Spectra, those delicate fingerprints of elements, are bound up with the electron behaviour. Much of what astronomy knows about distant stars and galaxies comes from reading the light associated with electrons in atoms and ions. So the electron is not only shaping the matter around us, it is helping us read the universe at large. Through it, we learn what stars are made of, how hot they are, how they move, and what processes unfold in places no human being will ever touch. For a supposedly small particle, it does get around. Yet perhaps the most important thing to understand about the electron is not merely that it does all these jobs, but that it appears to be fundamental. As far as experiments have been able to tell, the electron is not made of smaller pieces. It has no known internal structure. When probed at extremely high energies, it still behaves as if it is point-like in the sense relevant to present theories. This is extraordinary. Many things once thought basic turned out to be composed of smaller constituents. Molecules became atoms. Atoms became nuclei and electrons. Protons and neutrons became quarks. The electron so far remains itself. That does not prove with absolute metaphysical certainty that it has no deeper structure. Physics is careful about final declarations. But within the framework of the standard model, the electron is elementary. It is not built from smaller known parts. It is one of the ingredients out of which larger structures are made, not a structure made from something else. That gives it a special kind of purity in the theory, if one may use such a word without making particle physicists too nervous. And once you see the electron this way, as a fundamental lepton rather than just a handy bit of atomic decoration, the old schoolroom picture begins to look less like an explanation and more like a doorway. Helpful, yes. Final, not remotely. Not. It turns out that the particle we thought we knew is really a meeting point for several great themes in modern physics. It connects the history of discovery because it shattered the idea of the indivisible atom. It connects to quantum mechanics because its atomic behaviour forced a new framework for reality. It connects to chemistry because it governs bonding and structure. It connects to technology because its controlled motion powers modern civilization. It connects to the standard model because it belongs to a fundamental family of matter particles. And it connects to some of the deepest open questions still hanging over physics, because even now we do not fully know why this family exists in the form it does, or why the electron has exactly the mass and role it has. So when we say we're meeting the electron, the meeting is really a second introduction. The first was simple and useful. The second is quieter and more honest. The electron is not just a tiny negative charge. It is a stable fundamental lepton. It is identical to every other electron in the universe. It does not behave like a miniature planet. It occupies quantum states. It helps create the periodic table, the solidity of matter, the flow of current, the language of chemistry, and the readable light of the stars. It is both ordinary and astonishing, so familiar that it disappears into the background, and so important that without it the world would not resemble the one in which you are now sitting, listening, and perhaps feeling a little more suspicious of textbook diagrams than you did before. And once that familiar face begins to look slightly less familiar, a natural question starts to follow close behind. If the electron is one member of a deeper family, then what exactly makes a lepton in the first place? And what is it about this quiet particle that reveals the rules of that family so well as we keep going? Once we move beyond the electron as a familiar resident of the atom, something interesting begins to happen. The question is no longer simply what the electron does, but what kind of thing it is. That may sound like the sort of distinction made only by people who alphabetize their spice racks and enjoy the phrase fundamental ontology over breakfast. But in physics it matters a great deal. Because once you ask what the electron is in the deeper sense, you're no longer just talking about one particle, you're talking about a category, a family, a set of rules that place the electron among a small group of particles with a very particular identity. And that is where the lepton enters fully into view. At first, the word itself can feel slightly underwhelming. Lepton does not arrive with the drama of black hole or supernova or antimatter. It sounds modest, slightly academic, perhaps a little too tidy. But it hides a serious piece of the universe. To say that the electron is a lepton is to say much more than that it is small or important or involved in electricity. It is to say that the electron belongs to one of the fundamental families of matter, one whose members share deep structural features, follow the same broad rules, and differ in very specific ways from other basic particles, especially quarks. So what makes a lepton a lepton? The most direct answer is that leptons are fundamental particles that do not feel the strong nuclear force. That one statement does a great deal of work. It tells us that leptons are not made of smaller known pieces within the standard model. It tells us that they are not bound together into protons and neutrons the way quarks are. It tells us that they occupy a different branch of the particle family tree. And from that point onward, the electron starts to look less like an isolated case and more like the nearest visible representative of a hidden clan. It helps to remember that modern particle physics is not just a list of tiny things, it is a map of identities. The important question is not only what particles exist, but how they relate to the fundamental interactions of nature. In the standard model, particles are sorted in part by the forces they respond to. Quarks feel the strong force, the electromagnetic force if they carry charge, the weak force, and gravity in the broad sense that everything with energy is affected by gravity. Leptons do not feel the strong force. Some feel the electromagnetic force because they carry electric charge, while others do not because they are neutral. All leptons, however, participate in the weak interaction, and all have mass, though some have very little. That difference from quarks is not a minor technical footnote. It shapes the role leptons play in the universe. Quarks are never found alone under ordinary conditions because the strong force binds them into larger composite particles such as protons and neutrons. Leptons, by contrast, can exist as individual particles. An electron does not need to be imprisoned inside a proton the way quarks are imprisoned inside hadrons. It can move through matter, leave atoms, enter currents, flow through circuits, and generally behave like a particle with a great many responsibilities and comparatively little supervision. There is something almost personality-like in that distinction, though of course particles do not have personalities unless you have been awake far too late reading particle physics papers and have started assigning temperaments to the standard model. Quarks are communal in the sense that they are confined into groups by the strong interaction. Leptons are more solitary. They are not held together by that same force. The electron in particular is free to participate in the electromagnetic and quantum structures that make chemistry and ordinary matter possible. That freedom is a crucial part of why the world looks the way it does. Still, not all leptons look like electrons. This is where the family resemblance becomes a little strange. There are 6 leptons in total if we count the 3 charged leptons and the 3 neutrinos. The charged leptons are the electron, the muon and the tau. The neutral leptons are the electron neutrino, the muon neutrino, and the tau neutrino. Right away, the pattern suggests that the universe may have a fondness for repetition. The electron is one version of something. The muon and tau are heavier versions of the same general type. The neutrinos accompany them as neutral partners. Why this repetition exists is one of those questions physics can describe beautifully, without yet being able to answer in the fully satisfying sense. The electron, muon, and tau all share several defining features. Each has the same amount of electric charge, namely 1 unit of negative charge in the convention used by physics. Each has the same intrinsic spin type. Each is treated as a fundamental particle. Each participates in the weak interaction. What separates them is mainly their mass. The muon is much heavier than the electron. The tau is heavier still. Because of that extra mass, the muon and tau are unstable. They decay into lighter particles. The electron, being the lightest charged lepton, has no lighter charged lepton available to decay into, while conserving the necessary quantities, and so it appears stable. This is one reason the electron remains in the everyday world while the heavier charged leptons do not. They are real, but brief. The electron is real and persistent. This idea of persistence is worth pausing over. The electron is not more fundamental than the muon or tau. It is simply lighter and stable. That can feel almost unfairly practical. The universe has produced multiple versions of the charged lepton, but only the lightest one gets to become a permanent part of atoms, chemistry, and life. The heavier ones appear in cosmic rays, particle accelerators, radioactive processes, and energetic environments, then vanish. They are like architectural prototypes that still exist but do not get used in the final home. Nature built them anyway. Now, if the charged leptons are already a little puzzling, the neutrinos make the family even stranger. They are leptons too, but they carry no electric charge. They do not interact electromagnetically. That means they do not participate in chemistry, do not orbit nuclei in atoms, do not light up electronics, and do not advertise their presence in the way electrons do. They interact through the weak force and gravity, and because the weak force is, as the name politely suggests, not especially forceful over ordinary distances, neutrinos are spectacularly difficult to stop. Vast numbers of them pass through your body every second without leaving any obvious trace. They are members of the same fundamental family as the electron, and yet they are so elusive that calling them shy barely begins to cover it. So if we gather all of this together, what truly defines a lepton? Not charge alone, because neutrinos are neutral. Not stability, because the muon and tau decay. Not visibility, because neutrinos are practically the introverts of the particle world. The defining idea is deeper. A lepton is a fundamental matter particle that does not participate in the strong interaction, and that belongs to one of the 3 lepton generations in the standard model. That is the formal picture. But the lived meaning of it, if one can say such a thing about particle physics without sounding overly fond of it, is that leptons form a branch of matter that remains outside the quark world, while still helping build the universe in essential ways. At this point, it is useful to notice how much modern physics depends on classification through symmetry and interaction rather than appearance. We cannot line up particles on a tiny shelf and admire their shapes. The electron does not come with a visible label attached saying lepton first generation charged, spin 1/2, stable. Please handle with quantum mechanics. Instead, we infer its identity from behavior, how it responds to fields, what conservation laws it obeys, what interactions it enters, what transformations it can undergo. In that sense, particle identity is less like recognizing a face, and more like recognizing a role in a very exact play. One of the most important of these roles is the way leptons fit into generations. The standard model organizes matter particles into 3 generations, and each generation contains a pair of quarks and a pair of leptons. The first generation includes the electron and the electron neutrino. The second includes the muon and the muon neutrino. The third includes the tau and the tau neutrino. The pattern is elegant enough to be satisfying and mysterious enough to be mildly annoying, which is a combination physics often achieves with remarkable consistency. We can write the pattern down, we can test it experimentally. But the deeper reason for 3 generations rather than 1 or 4 or 12 is not yet fully understood. If you are wondering whether the universe could not have made do with just the electron and skipped the muon and tau entirely, you are in excellent company. Physicists have asked essentially that question in more technical language for a very long time. The famous reaction on discovering the muon was, in spirit, who ordered that? Ordered. It remains one of the more relatable moments in particle physics. The muon is like an electron that wandered in wearing heavier boots, and then left before anyone could properly question it. The tau does much the same, but with even more mass and less patience. And yet these heavier leptons are not mistakes. They are built into the structure of the standard model. They can be created and detected. Their properties fit the pattern. They tell us that the electron is not unique in type, only in its role as the light-stable representative of its class. Once you accept that, the electron begins to look slightly different. It is not the definition of a lepton. It is an example of one, albeit the example most familiar to us because the visible world has made extensive practical use of it. There is another important feature here, one that takes us from particle family resemblance into the deeper logic of interactions. Leptons carry what physicists call lepton number, a kind of quantum bookkeeping label associated with the family. In ordinary processes, total lepton number is conserved. There are also generation-specific lepton numbers that were once thought to be separately conserved in all cases, though neutrino oscillations have shown that nature is a little more flexible than that. The details are subtle, but the main point is that leptons are governed by conservation rules that help define their identity and constrain what transformations can happen. Physics, as ever, is not just about what exists, it is about what is allowed. Allowed and not allowed are the quiet backbone of the subject. A great many things we might casually imagine never happen because they violate some conservation law, symmetry condition, or interaction rule. The electron does not simply decay into whatever would be convenient. The muon decays in specific ways because only certain outcomes preserve the necessary balances. Neutrinos change flavour as they travel, but within rules that can be described and tested. What makes a lepton is therefore not only a list of traits, but also a pattern of permissions and restrictions. The family is defined as much by the laws it obeys as by the properties it carries. It is also worth saying that in modern quantum field theory, the notion of a particle sits inside an even deeper framework. Electrons are excitations of the electron field. Muons are excitations of the muon field. Neutrinos arise from their own fields. In that language, a lepton is not merely a tiny object floating through space, but a quantized excitation of a fundamental field with specific transformation properties under the symmetries of the standard model. This is the sort of sentence that can make a room become suddenly very quiet, but it matters because it pushes us beyond the little billiard ball picture once and for all. The lepton is not a bead. It is a mode of the universe behaving in a particular lawful way. Now, one might reasonably wish that the universe had chosen a more visually cooperative method of existence, something with labels, colour coding perhaps, a small explanatory note pinned to each atom. But instead we get fields, symmetries, generations and conservation laws, which is beautiful in its own right, though admittedly less convenient for sketching on a napkin. Even so, the deeper picture helps explain why the electron is not just a household particle, but a member of a mathematically structured family. The lepton is defined by its place in that structure. It is elementary. It has half-integer spin. It does not feel the strong interaction. It participates in the weak interaction. It appears in one of three generations. It may carry electric charge or be neutral. Those are not random checkboxes. Together they define a branch of matter that runs parallel to the quark branch and complements it in the architecture of reality. This complementary role becomes especially important when we think about what matter actually is in the world around us. Ordinary atoms are made from nuclei containing quarks bound into protons and neutrons, surrounded by electrons. In that sense, ordinary matter is built from both major classes of matter particles. Quarks alone would not make chemistry. Electrons alone would not make nuclei. The world requires both branches, each playing a different role. The quarks provide the heavy central cores of atoms. The electrons provide the surrounding structure that makes atoms interact, bond, and form the rich complexity of materials and life. So the lepton is not merely an optional addition to the particle menu, it is one of the reasons matter becomes interesting. And still there remains the quiet oddness that the neutrinos, though leptons, do not join atoms in the way electrons do. Their near invisibility reminds us that family membership in particle physics is not about having the same everyday function. It is about sharing a deeper type of identity. The electron is a lepton we meet constantly. The neutrino is a lepton we mostly infer. The muon is a lepton that arrives dramatically and leaves quickly. The tau is even briefer. Together they tell us that a lepton is not a single behaviour but a fundamental template expressed in several forms. Perhaps that is why the lepton family feels both elegant and unfinished. It is elegant because the pattern is clear. Charged lepton with neutral partner, repeated 3 times. It is unfinished because the existence of those repetitions still asks for explanation. Why these masses? Why these generations? Why this arrangement? Physics can tell us what makes a lepton in the operational sense. It can tell us how leptons behave, how they differ from quarks, how they fit into the standard model, how they interact, and how they are observed. But the deeper why of the family structure remains partly out of reach. The pattern is there. The final story behind it is not yet complete. That incompleteness is not a flaw. It is one of the reasons the subject remains alive. Science is most interesting not when every drawer is neatly labelled and closed, but when the cabinet is beautifully organised and still contains one locked compartment. Leptons are like that. We know enough to classify them with great precision. We know enough to build technologies and experiments around them. We know enough to say exactly what distinguishes them from other particles, and yet they still leave us with a set of unanswered questions that feel fundamental rather than decorative. So when we move beyond the electron and ask what makes a lepton, the answer is not just that the electron has relatives. It is that the electron belongs to a deeper category of matter, defined by its lack of strong interaction, its fundamental nature, its place in one of 3 generations, and its role within the symmetries and conservation rules of the standard model. The electron is the nearest and most familiar member of that family, but the family itself stretches into stranger territory, toward heavier charged cousins and nearly invisible neutrinos, all carrying the same underlying signature of leptonic identity. And once that family is in view, it becomes difficult not to look at its members one by one and ask how the universe ended up with such an odd set of close relations, why one stays, why 2 vanish, and why the quietest ones of all can pass through worlds almost untouched as we turn to them next. And this is where the lepton family stops looking neat in the way a textbook likes and starts looking neat in the way nature often prefers, which is to say, patterned, consistent, and just odd enough to keep everyone from becoming too comfortable. Once you realise that the electron is not alone, the immediate temptation is to assume its relatives must be more or less what you expect. Perhaps slightly different versions. Perhaps a few technical variations. Perhaps the sort of family resemblance that lets you nod politely and move on. But the leptons do not really allow that. They are a small family, yes, but a very strange one, and the more closely you look at them, the more you begin to feel that the universe has repeated itself with a purpose it has not yet fully explained. The full lepton family consists of 6 particles in ordinary counting, or 12 if you include the corresponding antiparticles, which is a perfectly respectable thing to do, but would make introductions feel a little crowded. There are 3 charged leptons and 3 neutrinos. The charged leptons are the electron, the muon, and the tau. The neutrinos are the electron neutrino, the muon neutrino, and the tau neutrino. Those names are already a clue to the deeper structure. Nature has arranged them in 3 generations. Each generation contains 1 charged lepton and 1 neutrino partner. The pattern is clear. What remains unclear is why the pattern exists at all. The first generation is the one that builds the ordinary world as we know it. Its charged member is the electron. Its neutral partner is the electron neutrino. The second generation contains the muon, and the muon neutrino. The third contains the tau and the tau neutrino. In broad outline, the charged members of the family all behave like heavier or lighter versions of the same basic thing. They carry the same amount of electric charge, they have the same spin type, they follow the same general interaction rules, aside from the consequences of their different masses. The neutrinos are their neutral companions, much lighter, far harder to detect, and involved in the weak interaction in a way that makes them seem almost ghostly by comparison. If this arrangement feels a bit repetitive, that is because it is. And that repetition is one of the most important clues in the Standard Model. Physics is full of one-off discoveries, but when the same structure appears more than once, scientists start asking whether there is a deeper mechanism beneath it. In the Lepton family, the repetition is hard to miss. The electron, muon and tau are not random inventions. They are three versions of the charged lepton role. The neutrinos mirror the pattern. It is elegant, but also unsettling. The universe rarely gives you repeated rows in a table unless it wants you to notice them. Let us begin with the electron, since it is the family member with whom the world has made the longest and most practical acquaintance. The electron is light, stable, and deeply woven into ordinary matter. It binds atoms into molecules. It gives the periodic table its behavior. It flows through wires, shapes chemical reactions, and helps determine the size and surface properties of atoms. If the Lepton family were a household, the electron would be the one paying the bills, fixing the lights, and keeping the entire place functioning while the others drift in and out under more unusual circumstances. The electron is also the lightest charged lepton, and that matters enormously. Because it is the lightest, there is no simpler charged lepton into which it can decay while preserving the relevant conservation rules. As far as present experiments can tell, the electron is stable. That stability is why it remains in atoms and in matter generally. If the electron decayed readily, the visible world would be a much less dependable place. Chemistry would not have the same structure. Atoms would not keep their familiar arrangements. The entire ordinary material world would become less ordinary very quickly. The electron neutrino, the neutral partner of the electron, is a much less obvious resident of daily life. It does not take part in chemistry. It does not carry electric charge. It does not sit in atoms as a quiet orbital companion. It moves through the world with astonishing indifference to most of what is in it. Neutrinos are produced in nuclear reactions, in the sun, in radioactive decay, in cosmic ray interactions, in reactors, in stars, and in other energetic processes. Vast numbers of them pass through your body every second, and almost all of them do so without leaving the slightest noticeable trace. If the electron is the visible working member of the family, the electron neutrino is the relative whose presence is felt mostly through very careful experiments and very patient inference. Then we arrive at the muon, and this is where the family starts becoming delightfully awkward. The muon is, in many ways, like a heavy electron. It carries the same electric charge. It has the same spin type. It participates in the same broad interactions, aside from the fact that it does not settle into atoms the way electrons do, because it is unstable and because its greater mass changes the scale of its behavior. The muon was discovered in cosmic rays, and its appearance puzzled physicists because it seemed to be an unnecessary duplication. The famous response, or at least the spirit of it, was essentially, why does this exist? That remains one of the more endearing reactions in science. The universe had provided a second charged lepton, and instead of immediate gratitude, it received a baffled stare. The muon is much heavier than the electron, and because of that, it decays. It does not hang around building chemistry or participating in the architecture of stable everyday matter. It appears in high-energy processes and then transforms into lighter particles. The exact details of its decay are governed by the weak interaction and conservation laws, but the practical picture is simple enough. The muon is real, measurable and important, but temporary. It is like an electron that arrived carrying extra mass and then discovered that the universe does not really allow that much excess baggage to remain indefinitely. Its neutrino partner, the muon neutrino, shares the elusiveness common to all neutrinos. It does not carry electric charge, it interacts weakly, it is difficult to detect, yet it is distinct. It belongs to the second generation, and for a long time neutrinos were treated as though each came with a fixed family identity that stayed put forever. Later discoveries complicated that picture in fascinating ways, but for the moment it's enough to say that the muon neutrino is not merely a duplicate of the electron neutrino with a different label pasted on. It participates in the structure of the generations and in the weak interaction in ways that matter deeply for how particle processes unfold. Then there is the tau, the third charged lepton, and the tau is where the family resemblance becomes almost excessive. It is again like a heavier electron, only now heavier still than the muon, and correspondingly less stable. It carries the same electric charge as the electron and muon. It has the same spin type. It belongs to the same broad class of fundamental particle, but it is so massive and so short-lived that its role in the ordinary world is even more fleeting. It does not build chemistry, it does not linger in matter. It appears only in sufficiently energetic processes and then decays rapidly into lighter particles. The tau is perfectly real, perfectly lawful, and absolutely not part of your furniture. Its partner, the tau neutrino, completes the third generation. For a long time it was the last of the neutrino family to be directly detected, partly because neutrinos are already difficult enough, and partly because the tau itself is brief and demanding in the sort of way experimental particle physics has learned to interpret as job security. By the time the tau neutrino was confirmed, the family picture had become impressively complete. 3 generations, 3 charged leptons, 3 neutrinos, clear structure, no immediate explanation. That unanswered why is one of the reasons this family remains so interesting. If the electron alone existed, we could imagine a simpler universe. Charged lepton, neutral partner, done. But nature has not done that. It has instead repeated the pattern twice more, each time making the charged lepton heavier and more unstable, while the neutrino partner remains extremely light and elusive. This is not the kind of detail physicists are inclined to ignore. Repetition with variation is usually a sign that there is a deeper rule still waiting to be properly uncovered. One might ask whether the heavier leptons actually matter if they do not build the ordinary world. The answer is very much yes. They matter because they reveal the structure of the theory. They matter because they appear in high-energy environments and therefore help test the standard model. They matter because their properties, decays, and interactions give physicists ways to probe the weak force and to search for deviations from expected behaviour. They matter because they tell us the electron is not a singular miracle, but one instance of a broader particle type. And they matter because any complete theory of the universe ought to explain why the 3 generations exist and why their masses take the values they do. Mass, in fact, is one of the most striking differences inside the family. The electron is light enough and stable enough to become part of atoms. The muon is much heavier. The tau is heavier still. Those differences in mass are not cosmetic. They change lifetimes, decay channels, and the energy scales at which the particles appear. They determine which member of the family gets to participate in the ordinary world, and which ones remain mostly hidden in energetic phenomena. Yet despite those large mass differences, the family resemblance remains unmistakable. Charge, spin type, weak interaction pattern, generational organization. It is as though nature took one basic design and then built 3 versions, each heavier than the last, while refusing to explain its design choices in any reassuringly human way. The neutrinos add another layer of oddness because for a long time they were thought to be massless. That turned out not to be the whole story. We now know that neutrinos have very tiny masses, though much smaller than those of the charged leptons. This discovery came from one of the most remarkable features of neutrino behavior, namely oscillation. As neutrinos travel, they can change from one flavor into another. An electron neutrino can later be detected as a muon neutrino or a tau neutrino. This means that the flavor identities associated with the lepton generations are not frozen in quite the simple way early versions of the theory suggested. Neutrinos are, in a sense, more mobile in identity than their charged relatives. That is not merely a charming quirk. It was a major discovery because it showed that the original standard model needed extending in order to accommodate neutrino mass. Here again, the Lepton family proved to be more than a piece of tidy bookkeeping. It became a route to new physics, or at least a physics beyond the earlier simplest form of the standard model. The quietest members of the family turned out to be carrying one of the most important hints that our current picture, successful as it is not quite complete. There is also a practical lesson in how these particles appear in nature. The electron is everywhere because it is stable and because ordinary matter makes use of it. Muons are produced in cosmic ray showers when high-energy particles from space strike the atmosphere. Even now, muons are passing through you as a result of processes high above your head. That sounds dramatic, but they are a normal part of the particle environment of Earth. Taus are rarer in everyday surroundings because producing them requires more energy, and they vanish quickly once made. Neutrinos come from the sun, from reactors, from radioactive materials, from the Earth itself, from distant astrophysical events, and from the leftovers of energetic collisions across the cosmos. In other words, the family is not an abstract collection trapped inside textbooks. It is part of the active traffic of the universe. Still, despite all this activity, only the electron becomes a familiar structural component of your immediate world. That asymmetry is part of what makes the family feel so strange. Imagine a family in which one sibling builds cities, runs power grids, and manages nearly all of chemistry, while the second mostly arrives in bursts from the upper atmosphere and then disappears. The third shows up only in very energetic circumstances and vanishes even faster, and the remaining three walk through walls, planets, and bodies as though most of reality were made of fog. It would be a memorable reunion, but perhaps not a particularly restful one. The reason this family structure matters so much is that it reminds us not to mistake everyday importance for fundamental uniqueness. The electron matters most to us because we live in a world of stable atoms and chemistry. But at the level of the standard model, the muon and tau are not lesser forms of matter. They are equally fundamental charged leptons. Their role is different because of their mass and instability, not because they are somehow less basic. Likewise, neutrinos are not marginal merely because they are hard to detect. They are abundant, fundamental, and central to a great many processes in nuclear physics, astrophysics, and cosmology. There is a deeper pattern here as well, because the lepton generations mirror the quark generations. The standard model organizes matter into 3 generations overall, each containing 2 quarks and 2 leptons. This parallel structure suggests some hidden unity, some deeper framework in which quarks and leptons may be related more intimately than the standard model itself explicitly states. Various theories have explored such possibilities, though none has yet become the confirmed final answer. For now, what matters is that the Lepton family does not stand alone as a curious side pattern. It is part of the generational architecture of matter as a whole, and perhaps that is the quiet wonder of it. The family is small enough to memorize and strange enough to remain mysterious. The electron gives us matter as we know it. The muon gives us a heavier copy that proves the pattern is repeated. The tau extends the repetition once more and pushes it to even higher mass. The neutrinos, one for each generation, fill the picture with almost invisible partners whose behavior turned out to be subtler than expected. Together they make it clear that the universe is not built from one simple type of matter particle, but from families, repetitions, and interaction rules that seem both elegant and unfinished. So when we call this a strange little family, the strangeness is not decorative. It is built into the very structure of the theory. Why 3 generations? Why these masses? Why is only the first charged lepton stable enough to build the world around us? Why are neutrinos so light? Why do they oscillate? Why does the pattern repeat in such a clean way and then stop at 3? These are not side questions. They are central questions about why matter has the form it has. For now, though, one of the most useful things we can do is simply hold the family clearly in mind. The electron is the familiar one, light and stable. The muon is the heavier copy, real but short-lived. The tau is heavier again and briefer still. Each comes with a neutrino partner, neutral and elusive. Together they form the lepton branch of the matter particles in the Standard Model, a family whose members differ in mass and visibility but share a common underlying identity. And once that family picture settles into place, the next natural step is to look more closely at the properties that all these particles carry, the hidden features that define them beneath their names, their masses, and their odd family roles, as we move from the relatives themselves to the invisible identity card each lepton seems to carry wherever it goes. Once the family itself comes into view, the next question almost asks itself: if electrons, muons, taus, and neutrinos belong to the same broad group, then what is it that gives each lepton its identity in the first place? Not its name, of course, because nature is not in the business of attaching little labels to particles as they pass by. Not its reputation, because the electron is only famous to us because it is useful in ordinary matter. The deeper identity of a lepton comes from its properties, the features that determine what it can do, what it can respond to, how it behaves in fields, how it combines with other particles, and what kind of role it can play in the structure of the universe. This is where the subject becomes both more exact and more revealing, because for all the variety in the lepton family, there are a few hidden properties that matter again and again. Charge is one of them, spin is another. And the way a lepton interacts with light, or does not interact with it, tells you a great deal about what sort of particle you're dealing with. These are not decorative details. They are the difference between a particle that helps make atoms, electricity, and chemistry possible, and one that slips through whole planets almost unnoticed. It is tempting at first to treat a particle as though its identity were just a matter of what it is made of. We do that all the time in ordinary life. Wood is wood because of its substance. Water is water because it is a particular material. But at the level of fundamental particles, identity is much more about properties than composition, because as far as we know, leptons are not built from smaller known parts. They are elementary in the Standard Model. That means their identity is not really about ingredients. It is about lawful traits, what charge they carry, what mass they have, what spin they possess, which forces they respond to, which conservation rules they obey. Those are the features that tell nature how to treat them. Charge is perhaps the easiest place to begin, because it is both familiar and powerful. We encounter electric charge early in life, even if not by name. A spark from a doorknob in dry weather, a balloon clinging to hair or fabric, the attraction and repulsion of electrically charged objects. And in school, the electron is often introduced as the negatively charged particle of the atom. That is true, but it is only the beginning of what charge means. To say that a particle has the electric charge is to say that it participates in the electromagnetic interaction. It can feel electric and magnetic fields. It can emit and absorb photons under the right conditions. It can be pushed, pulled, accelerated and organized by the same interaction that gives rise to light, electricity, magnetism, and much of the visible structure of matter. This already tells you something profound about the electron, the muon, and the tau. All three carry the same amount of electric charge. Not similar amounts, not approximate amounts, the same amount. That shared charge is one of the clearest signs that they belong to the same particle pattern. This sameness matters. It means a muon behaves like a heavy electron in electromagnetic fields. It means a tau does as well, within the brief window before it decays. If you did not know their masses and lifetimes, and only asked how they respond to electric charge, you would see a strong family resemblance. The universe has repeated the same electrical role 3 times while changing the mass. That is one of the reasons the Lepton family feels so structured. The charge members are not random inventions. They are different versions of one design. The neutrinos immediately complicate this picture in an interesting way, because they do not carry electric charge at all. They are neutral leptons. This means they do not take part in the electromagnetic interaction in the ordinary direct sense. They do not respond to electric fields the way electrons do. They do not emit or absorb light in the same familiar way. They do not get trapped into atomic structure. They do not help shape chemistry. In practical terms, this absence of charge is one of the main reasons neutrinos are so elusive. A charged lepton leaves obvious traces. It's obvious. It ionizes matter, bends in magnetic fields, and generally announces itself with more confidence. A neutrino slips through quietly because one of the most important everyday interactions is simply not available to it. This gives charge a kind of sorting power. The charged leptons enter one style of physical life, the neutrinos enter another. It is not that neutrinos are less real or less fundamental, they are simply missing one of the properties that makes particles easy for us to see and use. The electron becomes central to ordinary matter because it is charged, light and stable. The neutrino remains hidden because it is neutral, extremely light, and governed mainly by the weak interaction, which is not particularly forthcoming at ordinary scales. There is also something rather striking about how exact electric charge is. Every electron carries the same negative charge. Every muon and every tau carries that same charge as well. This precision is not just convenient. It is one of the basic regularities of nature. The universe does not seem to allow a slightly more negative electron or a somewhat indecisive muon. The amount is fixed. That exactness is part of what makes the world so orderly. Chemical structure, electrical behavior, and atomic organization depend on it. If charge were loose or approximate, the universe would be a much less disciplined place. Once charge is in view, light enters naturally, because light is the familiar face of the electromagnetic interaction. In modern physics, light is described in terms of photons, the quanta of the electromagnetic field. Charged leptons interact with that field. That is why electrons can absorb and emit light when their atomic states change. It is why they are so central to the spectra of atoms. It is why so much of the visible world is readable through electron behavior. The story of light in ordinary matter is, to a very large extent, a story about electrons. When atoms emit light, it is often because electrons are shifting between allowed states. When materials absorb light, electrons are frequently involved there too. The colours you see, the glow of heated matter, the signatures of elements in stars, all of this is deeply tied to charged leptons, and above all to the electron. The muon and tau also interact electromagnetically because they carry charge, but they do not shape the visible world the same way because they are not stable residents of ordinary atoms. The electron remains the everyday specialist. It is the charged lepton that the world actually keeps around. Still, the family resemblance is important, because it tells us that the ability to interact with light is not uniquely electron-like. It is a property of the charged lepton pattern. The difference is that only the lightest charged member becomes a lasting part of ordinary matter. Neutrinos sit outside this conversation in an almost stubborn way. They do not talk to light directly as charged leptons do. They are not part of the ordinary electromagnetic business of atoms, molecules, wires, and surfaces. If charged leptons are the visible workers of the Lepton family, neutrinos are the ones standing just outside the lit room, still present, still fundamental, but not participating in the same way. This is why a neutrino can travel through dense matter with hardly any interruption. It is missing one of the most socially active traits in the particle world. And yet charge alone does not define a lepton. It cannot, because neutrinos are leptons too. So we have to look at another deeper property, one that is harder to picture and even more fundamental in some ways, Spin. Spin is one of the most important and one of the most misleadingly named properties in quantum physics. The ordinary word suggests a little object physically rotating around an axis, like a top or a planet. That is not what is happening here. A lepton is not a tiny ball spinning in space in the everyday mechanical sense. If you push that image too far, it causes more confusion than clarity. But the term survived, and so we live with it. Spin is an intrinsic quantum property. It is part of what a particle is, built into its identity from the start. All leptons have the same spin type. They are particles with spin 1/2. That places them in a broader category called fermions, though even without the category name, the consequences are what really matter. Particles of this spin type obey a very particular set of statistical rules. They do not pile into exactly the same quantum state under the same conditions. This is one of the reasons electrons build layered atomic structures rather than all collapsing into a single lower state. It is one of the reasons the periodic table exists in the shape it does. It is one of the reasons matter has texture, stability, and complexity instead of becoming a far simpler and less interesting soup. That is an extraordinary consequence for a property that cannot be seen directly. Spin is not just a technical label. It determines how a particle participates in the architecture of matter. Because electrons have spin 1/2, they obey the exclusion principle. Because of that exclusion, electrons arrange themselves in atoms in orderly patterns. Because of those patterns, chemistry becomes rich and structured. And because chemistry becomes rich and structured, molecules, materials, living systems, and the ordinary world become possible. A hidden quantum property ends up shaping almost everything you consider normal. The same is true in principle for the muon and tau, because they are also spin 1/2 leptons. If they were stable constituents of ordinary atoms, they would follow the same broad statistical rules. Their heavier masses would change the details, but their quantum character would remain that of fermions. The fact that the universe does not make long-term use of them in the same way is not because their spin is wrong. It is because their masses and lifetimes place them elsewhere in the cosmic order. Neutrinos too share this spin type. They're also fermions. That means the family resemblance runs deeper than charge. In fact, spin helps define the family more fundamentally than charge does, because charge splits the family into charged leptons and neutral leptons, while spin unites them all. Every lepton is a spin 1/2 matter particle. That shared identity matters because it links the electron not only to the muon and tau, but also to the elusive neutrinos. The family is not just one of electrical behaviour, it is one of quantum character. Now one might reasonably ask how we know this if spin is not literal spinning and cannot be observed with the naked eye, which is a very sensible concern and one that particle physics has answered through the careful study of how particles behave in magnetic fields, in decays, in scattering experiments, and in quantum systems more generally. Spin reveals itself through consequences. It affects how particles align, how they combine, and what outcomes are possible in interactions. Physics often works this way. We do not need to see a property directly in order to infer it with great confidence. We need to observe the lawful effects it produces. This combination of charge and spin already goes a long way toward defining a lepton invisible identity. Charge tells you whether it joins the electromagnetic conversation. Spin tells you how it belongs to the quantum architecture of matter. Together they explain why the electron is both electrically active and deeply subject to quantum exclusion. They explain why the muon and tau behave like heavier charged cousins rather than entirely different species. They explain why neutrinos still count as leptons even though they sit out the electromagnetic side of family life. There is another subtle link between spin and light that is worth noticing. Charge particles with spin can carry magnetic moments, which means they have a built-in magnetic character. The electron is especially famous for this. Its behaviour in magnetic fields has been measured with astonishing precision. In fact, some of the most accurate agreements between theory and experiment in all of physics come from the magnetic properties of the electron. This is not just a triumph of careful measurement, it is also a sign that these hidden properties are not vague abstractions. They are exact features of reality, tested to extraordinary levels of detail. The muon has its own magnetic character as well, and the study of that property has become especially important because tiny deviations between theory and experiment might hint at physics beyond the standard model. This is one of the lovely things about particle identity. A property that sounds almost decorative to the newcomer can become a precision tool for testing the boundaries of theory. Spin, charge, and the magnetic consequences of their combination are not merely definitions. They are probes into whether our understanding of the universe is complete. And still, for all this exactness, one should not lose sight of the practical intuition underneath it. A lepton carries an invisible identity card. That card lists its charge, it lists its spin, it lists its mass, it determines which forces can talk to it, it determines what kinds of states it can occupy and what kinds of transformations are available to it. When the electron enters an atom, that identity card shapes chemistry. When a muon appears in a detector, that same kind of identity card shapes its track and its decay. When a neutrino passes through the Earth, its card explains why the journey is mostly uninterrupted. This is also where the phrase matter particle becomes more meaningful. Leptons are not just tiny objects, they are lawful patterns in the quantum fields of nature, each with a fixed set of properties. Those properties are what make them matter particles of a particular type. You could almost say that the universe reads the card before deciding how to behave, not consciously of course, but lawfully. Charge present. Electromagnetic interaction allowed. Spin 1/2. Fermi statistics apply. Neutral. Electromagnetic interaction absent. Mass tiny. Stability or decay determined accordingly. The world is built from these invisible rules. There is a great deal of elegance in the fact that the electron, which feels so central to ordinary life, is defined by the same hidden style of identity as the rest of the lepton family. It is not special because the laws apply differently to it. It is special because its particular combination of light mass, electric charge, spin 1/2, and stability makes it uniquely suitable for building the visible world. The muon shares much of that identity, but is too heavy and short-lived to take the same role. The tau is heavier still. The neutrinos share the spin and family membership, but without electric charge they cannot join the electromagnetic business of atoms and light in the same familiar way. This brings us back to light itself for a moment, because it is easy to forget how much of what we know about matter comes from watching charged particles interact with the electromagnetic field. The electron is readable to us because it moves charge around, sits in atoms, and participates in the emission and absorption of light. The neutrino is much harder to know because it stays out of most of that traffic. In a sense, the visible world favours charged leptons. It lets them write themselves into atoms, chemistry, and radiation. Neutral leptons remain in the background, real but harder to read, and perhaps that is part of why the electron can seem simpler than it really is. We meet it through its effects so often that it starts to feel familiar, but beneath that familiarity lies the same precise hidden identity that governs the whole family: charge, spin, interaction rules, quantum statistics. These are not decorative labels added after the fact. They are the reasons the family exists in the form it does. There is also a quiet lesson here about how modern physics understands reality. The deepest truths are often not visible traits, but mathematical and behavioural ones. The electron does not wear its spin on the outside. The neutrino does not advertise its neutrality with a badge. We infer these things because the universe behaves as though they are true, over and over, with remarkable consistency. Identity at this level is not about appearance. It is about lawful participation. A lepton is what it is because of how it can act, and how it must act. That is why the family can look repetitive and still remain mysterious. The charged leptons all carry the same electric charge. All leptons share spin 1/2. Yet the masses differ enormously, and only one charged member becomes a stable feature of ordinary matter. The invisible identity card contains both the similarities that unify the family and the differences that split their roles. The electron becomes everyday matter. The muon becomes a heavier temporary visitor. The tau becomes an even briefer one. The neutrinos remain abundant but quiet, difficult to catch and difficult to stop. So when we speak of the lepton's invisible identity, we are really speaking of the hidden structure that lets the universe tell these particles apart while also recognizing them as relatives. Charge decides whether they enter the electromagnetic world of light and atoms. Spin decides how they fit into the quantum order of matter. Together, these properties help explain why the electron is so useful, why the neutrinos are so elusive, and why the family resemblance runs deeper than anything a simple picture of tiny dots could ever show. And once you begin to see leptons this way, not as isolated little particles but as bearers of a precise hidden identity, it becomes easier to notice the next question waiting just behind them. If these particles have such a clear internal logic, then what exactly separates them from the other great branch of matter particles, the quarks, whose lives are governed by a very different set of rules, even when the family resemblance on paper seems at first surprisingly close? Now that the leptons have started to look less like isolated particles and more like a family with a shared identity, it becomes easier to notice the other family standing nearby. Because the standard model does not build matter out of leptons alone. It also includes quarks, and at first glance the two groups can seem oddly similar. Both are fundamental matter particles in the standard model. Both come in 3 generations. Both have spin 1/2. Both help build the universe as we know it. If you are only skimming the cast list, you might be forgiven for thinking they are variations on the same theme. But once you look more closely, the differences become decisive. Leptons and quarks live by different rules. They do not occupy the same role in matter. They do not interact in the same way. They are not free to move through the world under the same conditions. And some of the most important features of ordinary reality depend on exactly that difference. This matters because one of the easiest mistakes in particle physics is to imagine that all fundamental particles are just tiny interchangeable ingredients, as though the universe were built from one general purpose, microscopic gravel, and everything else were merely arrangement. That is not how it works. The fundamental particles are not all variations of the same thing in any simple sense. Their identities come with different permissions, different restrictions, and different interactions. A quark is not simply a lepton with extra mass or extra enthusiasm. A lepton is not a quark that has chosen a quieter lifestyle. They belong to separate branches of matter, and the hidden rules dividing those branches shape nearly everything. The first and most important distinction is the strong nuclear force. Quarks feel it, leptons do not. That single fact has consequences that ripple through all of particle physics. The strong force is the interaction that binds quarks together into composite particles such as protons and neutrons. It is enormously powerful at short distances and behaves in a way unlike any force in ordinary daily life. If you pull quarks apart, the force between them does not simply fade into nothing the way one might casually expect. In fact, the energy in the interaction can increase in such a way that quarks remain confined into bound states. This is one of the defining features of the quark world. Quarks are not found roaming freely under ordinary conditions. They live inside larger composite particles called hadrons. Leptons do not have this problem. Or rather, they do not have this feature. They do not participate in the strong force, so they are not confined in the same way. An electron can exist as an individual particle. A muon can exist as an individual particle. A neutrino can pass through the Earth as an individual particle, which is not exactly polite, but it is certainly free. This freedom is not a small technical distinction. It is one of the main reasons leptons and quarks play such different roles in the world. Take the proton, for example. The proton is not fundamental in the Standard Model. It is made of quarks held together by the strong interaction. The neutron is the same in that sense. So when you look at the nucleus of an atom, you are looking at a structure built from quarks. But when you look at the electrons associated with that atom, you're looking at fundamental leptons. Already the atom contains both branches of matter, one composite and strongly bound at the centre, the other fundamental and non-strongly interacting in the surrounding quantum structure. Ordinary matter is a partnership between these two different kinds of ingredient. This means that quarks and leptons differ not just in theory, but in the very architecture of matter. Quarks build the heavy central core of atomic nuclei through protons and neutrons. Leptons, especially electrons, shape the atom outer structure, chemical behaviour, and electromagnetic life. If quarks are the dense internal framework of ordinary matter, leptons are the active outer layer that makes matter chemically interesting and electrically responsive. Another major difference lies in electric charge. Leptons carry either no electric charge or one full unit of negative charge in the case of the charged leptons. Quarks, by contrast, carry fractional electric charges. Some quarks have a charge of 2/3 of the electron charge in magnitude, while others have 1/3 in the opposite sign. This is one of those facts that sounds almost mischievous when first encountered. One does not naturally expect nature to divide charge into thirds at the fundamental level, and yet that is exactly what quarks do. Now, these fractional charges are not usually seen in isolation, because quarks are confined inside hadrons. Protons and neutrons have overall charges that come out in whole units, because of how the quark charges combine. A proton ends up positively charged, a neutron ends up neutral. This is part of why the world of nuclei feels clean and stable in charge, even though its constituents are carrying these more exotic fractional values. Leptons, by comparison, are simpler in this respect. The electron has one full unit of negative charge. The neutrinos have none. No thirds, no balancing act required. Then there is the question of what kinds of composite structures the particles can make. Quarks combine into hadrons. They form protons, neutrons, and a whole zoo of other particles under high energy conditions. Leptons do not combine into hadrons because they do not carry the strong charge required for such binding. They may interact with other particles, they may form bound states in broader systems such as atoms, and they may be created or destroyed in certain processes, but they do not clump together under the strong interaction into little strongly bound families of their own. There is no lepton equivalent of a proton in the same sense. This makes the quark world feel more crowded and more internal, while the lepton world feels more solitary and more directly accessible. Even that phrasing is a bit anthropomorphic, but it captures the broad difference. Quarks are never really met alone in ordinary circumstances. We infer them through deep scattering experiments, high-energy collisions, and the structure of the hadrons they compose. Leptons, especially electrons, are encountered much more directly. Current in a wire involves electrons. Beta decay can emit electrons. Muons can travel through detectors. Neutrinos can in rare cases be caught interacting as individuals. The lepton does not have to be unpacked from a larger strongly bound object in the way a quark does. There is another hidden rule at work here, one that particle physicists somewhat misleadingly call colour. This has nothing to do with visual colour in the ordinary sense. No one is suggesting that quarks come in cheerful shades like paint samples. Colour charge is the name given to the kind of charge associated with the strong interaction. Quarks carry it. Leptons do not. That is why quarks are pulled into the strong interaction and leptons are not. The term colour survives because physics often names things quickly and then keeps the name forever, even when it causes generations of students to imagine particle physics in the style of an overcomplicated art supply catalogue. Because quarks carry colour charge, they interact through the particles that mediate the strong force. Because leptons do not, They are excluded from that entire form of interaction. This difference has enormous consequences. It is why quarks remain confined. It is why hadrons exist. It is why nuclear matter has the structure it does. And it is why leptons can stay out of that business altogether and instead participate mainly in electromagnetism and the weak interaction, depending on the specific lepton. One could almost say that quarks live in a more socially demanding part of the particle world. They are forced into close association by the strong interaction. Leptons, by contrast, have a more independent existence. That independence is especially important for the electron, which can occupy atomic states without being trapped inside the nucleus, and for the neutrino, which can travel extraordinary distances through matter with barely any interruption. A quark could never behave that way. Its life is governed by a completely different set of constraints. Yet for all these differences, quarks and leptons still share some broad structural features, and that is part of what makes the contrast so interesting. Both come in generations. The first generation of quarks contains the up and down quarks, which are the ones that build protons and neutrons. The first generation of leptons contains the electron and the electron neutrino. The second and third generations repeat the pattern with heavier versions. So the standard model has this curious parallelism. Matter comes in two large families, each arranged in 3 generations, each with a repeated pattern of masses and partners, and yet each family obeys a different interaction logic. That parallel structure has invited speculation for decades. It suggests that quarks and leptons may be related at some deeper level not fully visible in the standard model as it stands. Perhaps they emerge from a more unified theory. Perhaps the generational repetition hints at hidden symmetries or earlier conditions in the universe. Perhaps the division between the families is part of a larger pattern not yet fully uncovered. Physics has proposed various possibilities, but so far the standard model remains the best experimentally confirmed framework, and within it the difference between quarks and leptons is fundamental. Another difference worth noticing is how the two families contribute to mass and stability in ordinary matter. Most of the visible mass of ordinary matter does not come directly from the bare masses of the quarks inside protons and neutrons. Much of it comes from the energy associated with the strong interaction that binds them together. The proton is a strongly interacting composite object, and its mass reflects more than just the individual quark masses. Electrons, by contrast, are fundamental leptons, and their mass is simply their own intrinsic property within the standard model. The electron contributes relatively little to the total mass of an atom, even though it contributes enormously to the atom's size, chemistry, and behavior. This is one of those cases where everyday intuition misleads us. We tend to think the biggest influence should come from the heaviest component. But in atoms, the heavy nucleus gives most of the mass, while the electrons largely determine how the atom behaves in chemistry and how matter interacts. The quark-built core gives weight. The lepton-built outer structure gives much of the character. Both are essential, but in very different ways. There is also the question of decay and transformation. Quarks can change flavour through the weak interaction, and leptons can as well in their own way, particularly through neutrino oscillation and charge lepton decays. But the rules are different in detail, and the strong interaction adds an extra layer of complexity to quark behaviour. Because quarks abound inside hadrons, the observable outcomes often involve composite particles transforming, fragmenting or decaying through patterns that are more complicated than those of isolated leptons. A muon decay is, in some sense, cleaner to think about than the decay of a strongly interacting hadron, because the muon is not carrying the baggage of confinement and internal quark dynamics. That cleanliness has made leptons especially valuable in experiments. Electrons and muons, for instance, often produce clearer signals in detectors than strongly interacting particles. They can travel through materials in more predictable ways. They are easier to identify. Neutrinos are the exception in the sense that they are hard to detect, but that difficulty comes from their weak interaction and neutrality, not from confinement. Quarks, by contrast, never simply leave neat, isolated quark tracks in detectors. They hadronize, which means they turn into sprays of composite particles. Even the way the two families appear in experiments reflects their different hidden rules. One might ask why the universe bothers with both families at all. Why not make everything out of quarks, or everything out of leptons? The answer seems to be that each family does something the other cannot. Quarks can build dense, strongly bound nuclear matter. Leptons can remain fundamental and mobile in ways that make atomic structure, chemistry, and weak interaction phenomena possible. A universe with quarks and no electrons would not have atoms in any familiar sense. A universe with electrons and no quarks would lack nuclei and therefore lack the heavy structured matter that chemistry depends on. Ordinary reality seems to require the partnership precisely because the rules are different. And that may be the most important point of all. The hidden rules that separate leptons from quarks are not academic distinctions. They are the reason there is a nucleus rather than just a cloud. They are the reason electrons orbit in quantum states rather than being swallowed into strongly bound matter. They are the reason protons and neutrons exist as composite particles, while electrons appear elementary. They are the reason chemistry can happen on top of stable nuclear scaffolding. In short, they are the reason matter becomes layered, structured, and interesting, instead of collapsing into something much simpler. There is also a kind of philosophical shift that comes with understanding this. Early scientific pictures of matter often suggest a hunt for one final brick, one ultimate little thing from which everything is made. Modern particle physics has replaced that dream with something more subtle. Reality is not built from one sort of fundamental object repeated endlessly. It is built from multiple kinds of fundamental entities governed by distinct interactions and symmetries. The deepest level we currently know is already a plural world. Quarks and leptons are both matter particles, but they are not interchangeable. They are roles in a larger structure, and the universe seems to require both scripts. This is part of why the electron becomes more impressive the better you understand quarks. The electron is not merely the negative particle in the atom. It is the non-strongly interacting counterpart to the quark world. It provides a different kind of matter, one that can remain free, can participate in atoms, can flow through conductors, can emit and absorb light in the context of atomic transitions, and can avoid the confinement that defines quarks. The electron seems simple only until you notice how much of its role depends on not being a quark. The neutrinos sharpen the contrast even more. They are leptons stripped of electric charge as well as strong interaction. They are almost all weak interaction and mass, with hardly any of the more visible forms of participation that make quarks and electrons so easy to notice. In a sense, they are the purest reminder that leptons occupy a separate domain from quarks. They are matter particles, yes, but matter particles living under an entirely different interaction profile. If quarks are dense, colourful, confined and communal, neutrinos are light, neutral, elusive and astonishingly free. So the hidden rules are these. Quarks carry colour charge and therefore feel the strong force. Leptons do not. Quarks are confined into composite hadrons. Leptons can exist as individual particles. Quarks have fractional electric charges. Charged leptons have whole unit charge in the familiar lepton sense, while neutrinos have none. Quarks build nuclei through protons and neutrons. Leptons build the outer quantum life of atoms and populate the weak interaction landscape. Both families are fundamental in the Standard Model. Both come in generations, both matter profoundly. But they matter in different ways because the rules governing them are different from the ground up. And once you see that clearly, the lepton family begins to look even more distinctive. Not just the electron, but the whole set. A branch of matter defined as much by what it does not do as by what it does. It does not feel the strong force. It does not carry colour charge. It does not get locked into quark-style confinement. That absence is not a lack. It is an identity. It is what allows the electron to build chemistry, and what allows the neutrino to ghost through the universe almost untouched. and among all those leptons, none displays that quiet strangeness more dramatically than the neutrino, which takes the lepton style of existence and pushes it to an almost absurd degree as we move further into the darkest and most elusive corner of the family. If the electron is the lepton we know best because it quietly helps build the ordinary world, then the neutrino is the family member that seems almost determined not to be known at all. It does not shape chemistry, it does not cling to atoms, it does not run through wires, light screens, or help hold the surfaces of everyday objects in place. It slips through the universe with such indifference to ordinary matter that for a long time it was more of a carefully reasoned suspicion than a comfortably observed fact. And yet the neutrino is not a minor particle tucked away in some obscure corner of theory. It is one of the most abundant particles in the cosmos. It is fundamental. It is active in some of the most important processes in stars, in radioactive decay, and in the early universe. It is, in other words, both central and elusive, which is a combination physics seems to enjoy perhaps a little too much. The neutrino earned its ghostly reputation honestly. Vast numbers of them are passing through you right now. Many come from the sun, others come from cosmic rays interacting with the atmosphere. Some come from the Earth itself through radioactive processes deep underground. Some are relics from events elsewhere in the cosmos. They move through your body, the walls around you, the ground below you, and much of the planet as though most matter were barely there. If an electron is sociable by particle standards, constantly joining the electromagnetic business of atoms and materials, the neutrino is the opposite. It keeps its distance. It does not carry electric charge. It does not participate in the strong interaction. And because of that, most of the usual ways particles make themselves known simply do not apply. This is what makes the neutrino such a distinctly Lepton sort of mystery. It takes the Lepton tendency toward independence and pushes it almost to the limit. The electron still talks to light. The muon still leaves tracks in detectors. The tau, brief as it is, can still be noticed through the charged particles it produces. The neutrino does not do even that most of the time. It interacts mainly through the weak force, and the weak force is not especially generous with opportunities. As a result, neutrinos can travel extraordinary distances through matter without being stopped. A light year of lead would give them pause more effectively than a wall, but even then some would likely carry on with the same cool lack of concern. And yet the neutrino was not invented merely to make experiments difficult. It was proposed for a very specific reason. In the early study of radioactive beta decay, physicists noticed something troubling. Energy seemed to be missing. When a nucleus emitted an electron in beta decay, the energy of the electron did not come out in a fixed amount as expected from a simple two-body process. Instead, it was spread across a range. That created a real problem. It looked as though energy conservation might be failing, which is the sort of result that does not make physicists relax into a pleasant evening. To rescue the situation, Wolfgang Pauli proposed that another particle must be involved, one that was carrying away the missing energy. It would need to be neutral, very light, and difficult to detect, otherwise someone would have noticed it already. Later, Enrico Fermi developed the theory more fully and gave the particle its name. Little neutral one, more or less. A charmingly modest label for a particle that would go on to haunt physics for decades. There is something deeply satisfying about this origin story. The neutrino was not first discovered by being seen directly. It was inferred because the universe was refusing to break one of its own rules. Energy had to go somewhere. Momentum had to balance. The decay only made sense if an unseen partner was slipping away with part of the total. So before it was a measured particle, the neutrino was a logical necessity. It entered physics as a way of saving order from apparent disorder, which is one of the more elegant ways for anything to arrive. Still, inferring a particle and detecting one are very different experiences. Because neutrinos interact so weakly, actually catching one took extraordinary patience and ingenuity. Experiments had to place large detectors near powerful sources such as nuclear reactors, where huge numbers of neutrinos are produced. Even then, interactions were rare. The neutrino could not be collected in some neat little box or bent in an electromagnetic field like a charged particle. It had to be awaited. Observers had to build a place in which, every so often, one neutrino out of an almost absurd multitude would finally interact and leave a trace. That difficulty is part of the neutrino personality, if one may be forgiven the phrase. It exists in staggering abundance and still behaves like a secret. That alone would make it interesting, but the neutrino also turns out to be essential for understanding stars. In the core of the Sun, nuclear fusion produces neutrinos in enormous numbers. These neutrinos stream outward and leave the Sun almost immediately, while light takes far longer to work its way out from the dense interior. That means neutrinos give us direct information about what is happening inside the Sun in a way ordinary sunlight cannot. They are messengers from the stellar core, and very efficient ones at that, though their communication style is regrettably minimal. For a while, however, the Sun introduced a fresh puzzle. Early experiments designed to count solar neutrinos found fewer than expected. This became known as the solar neutrino problem, and for a time it looked as though either our understanding of the Sun or our understanding of neutrinos was incomplete. As it turned out, the neutrinos were the more mischievous of the two. They were changing identity on the way from the Sun to Earth. This phenomenon is one of the most remarkable features of neutrinos. They oscillate. An electron neutrino produced in the Sun can later be detected as a muon neutrino, or a tau neutrino. In other words, neutrinos do not keep the same flavor identity in a rigid way as they travel. They can shift among the three known types. This was a profound discovery because it meant neutrinos could not be exactly massless in the simplest original picture. If they oscillate, then the relationship between their flavor states and their mass states must be more subtle. The neutrino was not only real, it was more complicated than expected. This discovery mattered far beyond neutrino physics. It showed that the simplest version of the standard model was incomplete. The theory had treated neutrinos as massless, but nature had other ideas. Their masses are tiny, incredibly tiny compared with the charged leptons, but apparently not zero. That may sound like a small correction, but in particle physics, tiny corrections often point toward very large questions. Why are neutrino masses so small? Why do they mix the way they do? Why is their behavior so different from that of the charged leptons? These are not decorative mysteries. They are clues that our current model, successful though it is, may be only part of a deeper story. There is also something wonderfully unsettling about the fact that the most elusive leptons turned out to be the ones quietly telling us our theory needed adjusting. The electron is visible in ordinary matter. The muon is catchable in detectors. The two can be inferred from energetic collisions, but the neutrino, the one most likely to slip through everything without comment, turned out to be carrying one of the most important messages. It is a recurring theme in science that the hardest things to notice are often the ones that change the picture most. If we step back for a moment, the neutrino identity card is a peculiar one. It is a lepton, so it has spin 1/2 and belongs to the matter particle family rather than the force-carrying particles. It does not carry electric charge. It does not feel the strong interaction. It participates in the weak interaction. It has a very tiny mass. It comes in 3 flavors associated with the 3 lepton generations, and, unlike the charged leptons, it is exceptionally good at passing unnoticed through matter. All of this makes the neutrino feel almost like the stripped-down version of a matter particle. It is matter with the loudest interactions removed. That has practical consequences for detection. To observe neutrinos, scientists build large and often rather dramatic detectors. Some are placed deep underground to shield them from other particles. Some use huge tanks of ultra-pure water or other materials, waiting for the rare flash of light or particle signal produced when a neutrino finally interacts. The irony is hard to miss. To detect one of the smallest and most elusive particles in nature, humans construct some of the largest and quietest instruments in experimental physics. There is something almost ceremonial about it. entire caverns prepared in the hope that a few neutrinos will, for once, stop being so reserved. And when they do interact, the results can be extraordinary. Neutrino detectors have observed particles from the Sun. They have observed neutrinos from cosmic ray interactions in the atmosphere. They have seen neutrinos from reactors and accelerators. They have even detected neutrinos from a supernova, giving direct evidence of processes deep inside a dying star. In such moments, the neutrino stops being merely an elusive annoyance and becomes a unique astronomical messenger. Because neutrinos escape dense environments more readily than light, they can carry information out from places that photons struggle to leave. They are not just hard to catch, they are worth catching precisely because they come from hidden places. The early universe, too, was full of neutrinos. In fact, there should still be a vast cosmic background of them left over from the hot young universe, somewhat analogous to the cosmic microwave background of light, though even harder to detect. Neutrinos have been part of the cosmic story almost from the beginning. Their tiny masses and great abundance mean they have played a role in cosmology, structure formation, and the thermal history of the universe. This is another of those neutrino tricks. A particle can seem almost absent from daily life while still being woven deeply into the history of the cosmos. There is also the matter of flavour, which sounds almost endearingly culinary, until one remembers it describes a quantum property of an extraordinarily shy particle: electron neutrino, muon neutrino, tau neutrino. These are the flavours, and they correspond to the 3 Lepton generations. But the neutrino does not keep flavour in the simple way one might expect. Because flavour states are mixed combinations of mass states, a neutrino travelling through space evolves in such a way that the probability of detecting one flavour or another changes over time. This is neutrino oscillation. It is one of the most elegant and conceptually satisfying behaviours in particle physics, though I suspect the neutrinos were not trying to be elegant so much as difficult. The existence of oscillation also teaches a useful lesson about identity in the quantum world. We often like particles to be one thing cleanly and permanently: electron, muon, tau, done. But neutrinos remind us that quantum identity can be layered. What a neutrino is at the moment of creation in one interaction is not quite the same as the basis in which it propagates through space. That subtle mismatch is what allows oscillation to occur. It is a deeply quantum form of restlessness. All this naturally leads to the question of why neutrinos are so light. The electron has a modest mass by particle standards, but the neutrino mass is far smaller. Much smaller than the masses of the charged leptons, much smaller than the masses of quarks. Nature has made neutrinos with a level of lightness that seems to be telling us something important, though exactly what remains uncertain. There are theoretical ideas involving deeper mechanisms beyond the standard model, and neutrinos often appear near the centre of such speculation, because their masses are so unusual. When a particle departs sharply from the broader pattern, physicists begin to suspect hidden structure in the theory. There is another unresolved issue as well. We know neutrinos are neutral, but there is a profound question about what kind of neutral particle they are at the deepest level. Are neutrinos distinct from their antiparticles in the same way electrons are distinct from positrons, or could a neutrino in some sense be its own antiparticle? This is not merely a technical curiosity. It connects to possible forms of mass generation and to major questions in particle physics and cosmology. Experiments continue to test these possibilities with great care. The neutrino, having already complicated the standard model once, may yet have further surprises stored away. And then there is the simple oddity of scale. Trillions of neutrinos can pass through your body every second, and almost none of them matter to your immediate experience. That is a very unusual relationship with reality. We are used to assuming that what is abundant will be noticeable, and what is rare will be hard to find. Neutrinos reverse that expectation. They are abundant and hidden. The room you are in is full of them. The earth is full of them. Space is full of them. The sun is sending them constantly, and still they remain among the hardest particles to study in detail. It is almost as though nature wanted one of its most common ingredients to keep a low profile. This makes the neutrino a particularly good example of how the universe can be both lawful and deeply unintuitive. The neutrino is not magical. It is not slipping through matter because it is breaking the rules. Quite the opposite. It slips through matter because it obeys the rules of its own identity exactly. No electric charge, no strong interaction. Very tiny mass. Weak interaction only. Given those properties, ghost-like behaviour is not mysterious at all. It is what should happen. What feels strange is simply that our human sense of importance is shaped by electromagnetic life. We notice particles that interact the way we do. We barely notice those that do not. That is why neutrino physics has such a curious emotional texture. On one hand, it is meticulous and technical, full of detector design, background suppression, weak interaction probabilities and careful statistical analysis. On the other hand, it carries this very human fascination with hidden traffic, things passing through us from the sun, particles born in collapsing stars crossing interstellar space, a silent flood moving through the world while almost everything in ordinary life remains unaware. It is difficult not to feel a little humbled by that. So the neutrino secret life is this. It is born in nuclear processes, in stars, in decays, in cosmic events. It moves through the universe with remarkable freedom. It changes flavour as it travels. It has a tiny mass where once we expected none. It helps us probe the sun, supernova, reactors, the atmosphere, and the early cosmos. It is both abundant and elusive, central and hidden, fundamental and still not fully understood. Among leptons, it is the quietest member of the family and perhaps the one most likely to force the deepest revisions in our theories. And after spending time with neutrinos, another question begins to press forward rather naturally. If the electron makes sense as the stable charged lepton of ordinary matter, and neutrinos reveal a subtle and mysterious neutral side to the family, then what are we to make of the heavier charged relatives, the muon and the tau, which seem to repeat the electron design without staying around long enough to join the ordinary world? A puzzle that leads directly into why those extra copies exist at all. By the time we reach the muon and the tau, the lepton family begins to feel less like a clean classification and more like a question staring back at us. The electron makes immediate sense to our everyday world. It is light, stable, and essential to atoms, chemistry, electricity, and the whole reliable business of matter behaving itself. The neutrinos, elusive as they are, at least fit into a useful role as neutral partners that show up in nuclear reactions in stars and in the weak interaction. But the muon and the tau do something far more awkward. They appear to be heavier copies of the electron and then, almost as quickly, they disappear. That is not a satisfying state of affairs if you're the sort of person who likes your universe lean and efficient. One charged lepton might feel sensible. 3 begins to look indulgent. The electron already handles the visible world very well. It builds atoms. It supports chemistry. It gives us currents in wires and the structure of molecules. So why does nature also include the muon and the tau? Particles with the same electric charge, the same spin type, and the same broad interaction pattern, but with much larger masses and much shorter lives. It is one of the most famous questions in particle physics precisely because it does not yet have a final answer. We know that muons and taus exist. We know how to produce them, detect them, and describe their behaviour with impressive accuracy. We know they are fundamental charged leptons, not made of smaller known parts. We know they fit into the 2nd and 3rd generations of the standard model. We know they decay through the weak interaction into lighter particles. What we do not know in the deepest sense is why the universe bothered to repeat the electron design at all. There is a certain honesty required here. Physics is often presented as a long list of solved facts, as if every particle came with a fully understood purpose. But the truth is more interesting. Sometimes a theory tells us what exists and how it behaves long before it tells us why the pattern is the way it is. The muon and the tau are exactly that kind of case. They are not accidents in the theory. They are built into the pattern. But the reason for the pattern itself remains one of the great unfinished questions. The muon was the first sign that the Lepton story was not going to remain comfortably simple. When it was discovered in cosmic rays, it did not slip neatly into a pre-existing need in ordinary matter. It was not required to explain chemistry. It was not sitting in atoms waiting to be named. It arrived as a heavier charged particle that looked strikingly like an electron in many of its properties, except for the rather important detail that it was much more massive and unstable. This was not the sort of discovery that makes a theory feel elegantly complete. It was the sort that makes people squint at the universe and ask whether it is absolutely sure about this. That reaction has lasted because the basic puzzle remains. The muon is like an electron that has been given extra mass without being given a stable job to justify it. It can be produced in energetic environments. It can travel through matter. It can be measured very precisely, but it does not settle into the everyday structure of the world because it decays. Left to itself, it turns into lighter particles. It is not built for permanence. The tau is the same sort of story taken even further. It is heavier still and even more short-lived. If the muon looks like an unnecessary heavier electron, the tau looks like the universe repeating the idea once more, just to make the puzzle impossible to ignore. And yet it would be wrong to say they have no role. The better way to put it is that their role is not the same as the electron's role in ordinary matter. Muons and taus matter enormously for the structure of the theory and for the ways we test it. They tell us that the electron is not unique in type. They reveal that charged leptons come in generations. They allow us to study the weak interaction in different mass regimes. They give particle accelerators and cosmic ray experiments new ways to probe fundamental laws. They may even offer clues to physics beyond the standard model if their behavior deviates, even slightly, from what current theory predicts. This is one of the strange features of modern physics. A particle can be essential to understanding reality without being essential to building your table, your lungs, or your coffee mug. The muon and tau may not be used in the construction of ordinary stable matter, but they are part of the deeper architecture of the laws that govern all matter. That does not answer why they exist, but it does remind us that usefulness to daily life is not the same thing as importance in the structure of theory. It helps to step back and look at the broader pattern. The standard model organizes the matter particles into 3 generations. Each generation contains 2 quarks and 2 leptons. In the lepton branch, that means electron with electron neutrino, muon with muon neutrino, tau with tau neutrino. The charged member gets heavier as you go from one generation to the next. The neutrino partner remains very light, though not massless. The pattern is repeated with remarkable consistency. That repetition is not random clutter. It is orderly enough to suggest a deeper reason. The problem is that we do not yet know what that deeper reason is. One possible temptation is to imagine that the heavier generations are somehow stepping stones, as if the universe started with the electron and then built improved or experimental versions. But that is not really how physics describes them. The muon is not a better electron. The tau is not the final deluxe edition. They are all fundamental particles of equal theoretical status within the standard model. The difference lies in mass and stability, not in how basic they are. The electron survives because it is the lightest charged lepton. The muon and tau decay because lighter available states exist for them to decay into, while preserving the required conservation laws. That is practical. It is not explanatory in the larger philosophical sense. So where does the extra mass come from? In the standard model, the masses of particles are connected to their interactions with the Higgs field. This gives us a mechanism by which different particles can have different masses. But a mechanism is not the same as a deep reason. The theory allows different lepton generations to couple differently and therefore acquire different masses. It does not tell us why those couplings take the values they do. Why the electron is light, The muon much heavier and the tau heavier still is part of what physicists call the flavor problem, which is really a polite way of saying the pattern is written down very clearly, but the reason behind it is still obscure. The word flavor in particle physics is one of those names that makes the subject sound more cheerful than it feels at 3 a.m, but it refers to different types within a family: electron, muon, tau, different flavors of charged lepton. The puzzle is that the flavors are not symmetric in mass, and the origin of those differences is not fully explained by the standard model itself. The model accepts the masses as input from experiment. It uses them brilliantly. It predicts behavior with them, but it does not derive them from some deeper necessity we yet understand. The muon and tau, in that sense, are reminders that a theory can be extremely successful and still incomplete at the level of ultimate explanation. There is another reason the heavier leptons are so interesting. Their very existence gives physicists a chance to check whether the laws really do treat the lepton family members equally apart from mass effects. In principle, the weak interaction should couple to the electron, muon and tau in a universal way once the mass differences are properly accounted for. This idea, often called Lepton universality, is one of the key organizing principles in the standard model. If careful experiments ever showed a robust violation of that pattern, it would be a major clue that new physics is hiding nearby. That is why the muon, in particular, has become the center of so much attention. Because it is heavier than the electron, it is more sensitive in certain experiments to the influence of possible new particles or subtle effects beyond the standard model. A heavier charged lepton is, in some ways, a more delicate probe of the vacuum and the underlying interactions. Tiny discrepancies in its magnetic behavior or in certain decay patterns might reveal cracks in the current framework. So even if no one can yet tell you why the muon exists at all, it may turn out to be one of the best tools for discovering what comes next. The tau offers something similar, though in a more difficult experimental package. Because it is so heavy and so short-lived, studying it is harder. It decays quickly into other particles, and that makes it both rich in information and inconvenient to handle. The tau can decay into hadrons, into lighter leptons, and into neutrinos in various combinations, which gives physicists a complex set of channels to analyze. This complexity is useful because it opens many windows onto the weak interaction and flavor structure. It is inconvenient because the tau does not exactly sit still and wait for a tidy interview. One way to think about the muon and tau is that they are like extra verses in a song whose melody we recognize, but whose purpose we do not fully grasp. The electron establishes the pattern, the muon repeats it with more mass, the tau repeats it again with even more mass. The pattern is too clean to be meaningless, but the theory does not yet tell us why the song needs 3 verses instead of 1. There is also a historical lesson in how these particles changed our picture of matter. If only electrons existed among the charged leptons, it might be tempting to think that ordinary matter had led us cleanly to the final answer. But the appearance of muons and taus forced physicists to accept that the fundamental world contains more than what everyday matter visibly uses. The universe is under no obligation to build itself in the most economical way for human intuition. It includes particles that appear mostly in high-energy environments, in cosmic rays, in accelerators, and in short-lived processes. Reality is not designed as an introductory course. It is broader than the visible layer of matter suggests. This becomes especially clear when we think about the early universe. In the hot, dense conditions shortly after the Big Bang, the heavier particles of the standard model would not have been rare curiosities. They would have been part of the active particle soup. At high enough energies, muons and taus can be produced readily. So while they may not be part of the stable furniture of the present-day world, they belong naturally to the fuller particle life of the universe under more extreme conditions. That does not explain why they exist, but it does remind us that judging a particle by its usefulness in your living room is perhaps not the fairest standard. There is another subtle point here. The existence of heavier generations is not limited to leptons. Quarks also come in 3 generations, with the second and third generations containing heavier versions that are not part of ordinary stable matter. This suggests that the repetition of generations is not specifically a Lepton oddity. It is a broader feature of the Standard Model. That may mean the answer to why muons and taus exist is tied to the deeper question of why matter comes in generations at all. The Lepton puzzle may be one piece of a much larger puzzle about family structure across the particle world. Some theoretical ideas have tried to explain this generational repetition through deeper symmetries, hidden structures, or more unified theories in which quarks and leptons emerge from a common underlying scheme. Others explore whether the pattern of masses and mixings might come from new fields or new principles not yet observed directly. There are even suggestions that the heavier generations may play a role in cosmological questions, perhaps indirectly through mechanisms that shape the matter content of the universe. But none of these ideas has yet become the confirmed final answer. For now, the muon and tau remain lawful facts waiting for a deeper reason. What we can say with confidence is that they are not disposable. Without them, the Standard Model would be simpler, but reality would not match it. They are part of the observed inventory of nature. They influence the outcomes of high-energy collisions. They appear in cosmic ray showers and in decays of other particles. They contribute to precision tests of the theory. They serve as stepping stones for understanding weak interactions, flavor structure, and possible physics beyond the Standard Model. In that sense, their existence is not a decorative surplus. It is a real, structural feature of the universe. Even their instability teaches something important. The fact that the muon and tau decay into lighter particles shows how the lepton family is ordered. Heavier charged leptons flow down towards lighter ones through the weak interaction. The electron sits at the bottom of that charged ladder. Stable, not because it is uniquely privileged in some mystical sense, but because there is nowhere lower for it to go among charged leptons. The muon and tau therefore help define the electron by contrast. Without them, the electron would look singular. With them, it looks like the surviving lightest member of a repeated pattern. This is where the question becomes almost philosophical. Do muons and taus exist because they serve some hidden purpose we have not yet uncovered? Or do they exist simply because that is the way the deeper laws happen to be arranged? Physics tries not to assign purpose in the human sense. It looks for mechanism, symmetry, and necessity. But there is still a meaningful version of the question. Is the generational structure something that had to be this way given a deeper theory? Or is it contingent, one possible arrangement among many? We do not know. And until we do, the muon and tau will remain some of the clearest reminders that description and explanation are not quite the same thing. There is also something quietly reassuring in the fact that physics is willing to leave such questions open. Rather than pretending the muon and tau are fully understood simply because their properties are measured, the field continues to treat their existence as a clue. That is science at its best. Not a catalogue of finished certainty, but a framework sharp enough to say exactly where the mystery still lives. So why do muons and taus exist at all? The honest answer is that no one yet knows in the deepest sense. They exist because the universe includes 3 generations of leptons, because the Standard Model describes them successfully, because experiments confirm them, because nature repeats the charged lepton pattern at higher masses. They may exist as part of a deeper flavor structure we have not yet uncovered. They may point towards symmetries or mechanisms beyond the Standard Model. They may be telling us that the visible electron is only the first line of a larger story. What we do know is that they are not meaningless duplicates. They are lawful members of the lepton family whose extra mass turns them into brief, but revealing participants in the particle world. And perhaps that is the right way to hold them for now, not as pointless excess, but as unresolved repetition. The electron gives the world its stable charged lepton. The muon and tau repeat the pattern with increasing mass and decreasing patience, and in doing so they force us to confront one of the most basic unanswered questions in particle physics. Why the families of matter exist in generations at all? And once that question settles in, it naturally leads toward the interaction that governs so much of lepton behavior beneath the surface. the quiet force responsible for decays, flavor change, and the subtle conversation these particles keep having with the universe even when no one is looking. By the time we arrive at the weak force, the Lepton family begins to feel less like a set of particles and more like a set of participants in an ongoing exchange. The electron, the muon, the tau, and the neutrinos are not just sitting in the universe carrying identities around like formal documents. They are interacting. They are transforming. They are involved in decays, scatterings, reactions in stars, radioactive processes in nuclei, and some of the most delicate forms of change known in particle physics. And beneath all of that sits the weak interaction, a force with a name that sounds almost apologetic until you notice how much of reality depends on it. The weak force is one of the 4 known fundamental interactions of nature. It does not dominate daily life the way gravity shapes the motion of large bodies, or the electromagnetic interaction shapes chemistry, light, and technology. It does not bind quarks together with the fierce insistence of the strong interaction. In fact, it is easy to miss altogether if you think only in terms of what you can feel directly. But that would be a mistake. The weak force is subtle, yes, but subtle is not the same as unimportant. If anything, the weak interaction is one of the best examples in physics of a process whose effects are everywhere even though its action is usually hidden. Leptons are especially tied to the weak force because every lepton participates in it. Charged leptons do. Neutrinos do. In fact, neutrinos are almost defined in practice by how completely they depend on it, since they do not carry electric charge and do not feel the strong force. The weak interaction is their main route into the rest of the universe. If electromagnetism makes the electron visible and useful in ordinary matter, the weak force makes the entire Lepton family dynamic. It allows particles to change type. It allows unstable leptons to decay. It allows neutrinos to interact at all. It sits quietly behind much of the motion and transformation in the particle world. To understand why this matters, it helps to begin with one of the most familiar weak processes in physics, beta decay. This is a form of radioactive decay in which a neutron in a nucleus turns into a proton while emitting an electron and an electron neutrino. Described that way, it almost sounds routine, which is one of the charming tricks of modern science. A process that completely changes the identity of particles can sound like a minor accounting adjustment if you say it calmly enough. But beta decay is remarkable. It shows that the weak force allows matter particles to transform in ways other interactions do not. The strong force binds. Electromagnetism arranges and pushes and pulls. Gravity curves and attracts. The weak force changes flavor. That is one of its most distinctive talents. It allows one kind of particle to turn into another. That is not a minor service. It is a profound one. Without the weak interaction, many particles would never decay. Nuclear reactions in stars would proceed differently or not at all in the forms we know. Neutrinos would become even more disconnected from the rest of physics than they already seem. The entire history of matter would change. Leptons feel this especially clearly because much of their family life is governed by the weak interaction. The electron is stable, but the muon is not. The tau is not. Their decays happen through the weak force. A muon can decay into an electron, a muon neutrino and an electron neutrino. The tau can decay into lighter leptons and neutrinos, or into hadrons and a tau neutrino depending on the channel. In each case, the weak interaction is the quiet machinery making the transformation possible. It is the reason the heavier charged leptons do not remain permanent residents of the particle world. This gives the weak force a very different personality from the other interactions. It is not mainly a force in the everyday push and pull sense. It is more like a mechanism of change. It acts at very short range. It involves very heavy messenger particles. It is responsible for processes that alter particle identity itself. If electromagnetism is the force of visible structure, the weak interaction is the force of hidden transitions. That short range is important. The weak force is called weak not because it is unimportant, but because under ordinary conditions its effects are much harder to notice. Part of that is because its messenger particles are very massive. The weak interaction is carried by heavy particles known as the W boson and the Z boson. Because these messenger particles are so massive, the weak force acts over an extremely short distance. You do not feel it across the room. It does not organise the visible surfaces of matter. It appears in processes that happen inside particles, nuclei, stars, detectors, and high-energy collisions. It is intimate rather than expansive. This is one reason neutrinos are so elusive. Since they interact only through the weak force and gravity is negligible at the level of single particles, the weak interaction is their only practical link to ordinary matter. But the weak force is short-ranged and difficult to trigger, so neutrinos can travel through enormous amounts of material before finally interacting. They are not refusing to participate, they are simply participating according to a very quiet set of rules. With charged leptons, the story is different because they also carry electric charge. The electron, muon and tau can interact electromagnetically as well as weakly. That is why electrons are so prominent in ordinary physics. That is why muons leave clean tracks in detectors. But beneath that electromagnetic visibility, the weak force is still there, governing certain decays and reaction channels. The muon is the clearest example. A muon moving through matter may behave like a heavy electron in many ways, but its mortality comes from the weak interaction. The universe does not keep muons around because the weak force gives them a route downward into lighter particles. That route downward is one of the most useful ideas in all of particle physics. Heavier leptons decay into lighter ones through the weak interaction, subject to the conservation laws and selection rules that make sure nature does not simply improvise. The electron sits at the bottom of the charged lepton ladder, stable because there is no lighter charged lepton available. The muon sits above it and decays. The tau sits above both and decays faster still. The weak force is what makes that ladder active. Without it, the lepton family would be frozen in a very different form. Neutrinos complicate the picture in a fascinating way, because they are also governed by the weak interaction, but they do not merely decay or scatter, they oscillate. A neutrino produced as one flavour can later be detected as another. This is not exactly the same as a charged lepton decay, but it is still part of the wider story of how the weak interaction is linked to lepton identity. Neutrinos are created and detected through weak processes, and the flavour labels that matter in those interactions are not perfectly aligned with the mass states through which neutrinos propagate. The result is that the weak force sees one kind of identity at the moment of interaction, while the neutrino itself evolves in a way that allows those identities to mix. This is part of what makes the weak force feel like a subtle conversation rather than a blunt shove. It does not merely transfer energy. It mediates translation between kinds of particle identity. It governs which leptons can appear together, which neutrinos are produced in which processes, how flavours are matched, and what changes are allowed. Physics here begins to look less like moving objects around and more like maintaining a very strict grammar. And grammar is not a bad analogy. The weak interaction has syntax. Not every sentence is allowed. Not every transformation can occur. The universe does not take a muon and casually turn it into anything that seems convenient. The decay products must preserve charge, energy, momentum, angular momentum, and the appropriate lepton accounting. The weak force is permissive in a specific way. It allows change, but only lawful change. That is why it feels so central to particle identity. It is the interaction that governs transformation without dissolving order. There is another reason the weak interaction matters to leptons. It helps shape the sun and the stars. In stellar fusion, the weak force plays an essential role in the processes that convert hydrogen into helium and release energy. One of the key early steps in the chain involves a proton effectively transforming through a weak process that produces a positron and a neutrino. Without the weak interaction, the sun would not shine in the way it does. That is an astonishing fact when you think about it. a force so hidden in daily life is central to the slow, steady burning of stars, including the one that warms the Earth and keeps the biosphere in business. The weak force also contributes to radioactive decay in unstable nuclei, which affects the heat of the Earth, the dating of ancient materials, the production of certain elements, and the operation of nuclear reactors. This is one of those moments where particle physics reaches directly into geology, chemistry, astronomy, and technology. The weak interaction is not an isolated curiosity tucked away in accelerator labs. It is part of the deep engine of change across the universe. Leptons stand near the centre of this because they are often the outgoing messengers in weak processes. An unstable nucleus emits an electron and a neutrino. A muon decays into an electron and neutrinos. A tau decays into lighter leptons or other products through weak channels. Neutrinos stream away from stellar interiors and supernovae. Again and again, when the weak force goes to work, leptons are involved. They are its preferred messengers, witnesses, and outcomes. This connection is built into the Standard Model very deeply. The weak interaction couples to leptons in a structured way, pairing each charged lepton with its associated neutrino in what is often called a weak doublet. The electron goes with the electron neutrino, the muon with the muon neutrino, the tau with the tau neutrino. This pairing is not just naming convenience. It is part of how the weak force sees the lepton family. In a sense, the weak interaction organizes leptons generation by generation. That is one reason the family structure matters so much. It is not merely a classification after the fact. It is part of the interaction pattern itself. The heavy messenger particles of the weak force make that pattern concrete. The charged weak messenger allows changes between a charged lepton and its associated neutrino. This is how, for example, an electron neutrino can interact and produce an electron, or how a muon can decay and involve a muon neutrino. The neutral weak messenger, meanwhile, allows other weak interactions that do not change electric charge. Together, these channels make the weak force both versatile and highly constrained. It can change flavor in some contexts. It can scatter particles in others. It can produce or absorb leptons according to strict rules that reflect the underlying symmetry structure of the Standard Model. That underlying symmetry is one of the quieter triumphs of modern physics. What looks at first like a collection of arbitrary processes turns out to be organized by a deeper mathematical pattern in which the weak interaction and electromagnetism are related at high energies. This is the electroweak theory, one of the great successes of 20th century physics. It showed that the weak force and the electromagnetic force, which seem so different in ordinary life, can be understood as aspects of a unified framework under the right conditions. At lower energies, the symmetry is broken in such a way that the weak interaction becomes short-ranged and distinct, while electromagnetism remains long-ranged and familiar. This means the lepton family is participating in a conversation that is, at a deeper level, connected to light itself. The electron already made that obvious through electromagnetism, but electroweak theory reveals that the weak interaction is not a completely separate afterthought. It is linked to the broader gauge structure of the Standard Model. The universe, it turns out, is economical in its deeper mathematics even when it looks untidy in its particle inventory. There is something quite striking in the fact that the weak force treats handedness differently. This is one of its strangest features. In the weak interaction, left-handed and right-handed versions of particle states are not treated symmetrically. The weak force is selective in a way the other interactions are not. This was one of the great shocks of 20th century physics because it meant nature, at this fundamental level, distinguishes between mirror image arrangements. The universe is not perfectly indifferent to left and right in weak processes. For leptons, this handedness structure is built into how the weak interaction couples to them. It is part of the deep grammar of the theory. And though this may sound abstract, it has measurable consequences in decay patterns and in the behavior of weak interactions more generally. The weak force is not just subtle because it is short-ranged. It is subtle because its rules are asymmetric in a way that would have seemed almost impolite if nature had bothered to warn anyone in advance. This asymmetry also reminds us that the weak interaction is not merely a weaker version of something more familiar. It is its own kind of interaction with its own logic. The name weak can almost undersell it. It is not simply less intense. It is more selective, more structured, and more intimately tied to flavor change and particle transformation than the other forces. Leptons, because of their direct participation in it, reveal this very clearly. The weak force also plays a role in some of the most precise tests of the Standard Model. Measurements involving muon decay, tau decay, neutrino scattering, and weak interaction rates allow physicists to examine whether the theory holds exactly as expected. Any persistent deviation could point toward new particles, new symmetries, or new interactions beyond the current framework. This is especially interesting because the weak force is already the interaction through which many beyond Standard Model effects might first become visible. Its sensitivity to flavor, mass, and lepton family structure makes it a natural place to look for cracks. That means leptons are not only participants in the weak conversation, they're also our microphones. Through them we listen for imperfections in the theory. A slight mismatch in how often a certain decay occurs, a small anomaly in the magnetic behavior of the muon, a subtle inconsistency in neutrino oscillation data. These may be tiny details experimentally, but conceptually they can be enormous. The weak force is often where the Standard Model is tested hardest, because it governs so many delicate transitions. There is also a human side to all this, if one may put it that way. The weak interaction reminds us that some of the most important processes in the universe are not loud. They are not explosive by default. They are not visible in the ordinary sense. They happen in radioactive nuclei, in the core of the sun, in the decay of unstable particles, in the rare interaction of a neutrino deep underground. Their consequences are vast, but their action is quiet. The universe does not always announce its deepest changes with spectacle. Sometimes it makes them through a force most people never think about, acting over distances so short and in circumstances so hidden that we had to build an entire branch of modern particle physics just to hear it properly. So when we speak of leptons and the weak force, we are really speaking about the interaction that gives the lepton family its dynamism. It allows the heavier charged leptons to decay into lighter ones. It creates and detects neutrinos. It powers key nuclear reactions in stars. It governs radioactive change. It reveals the deep pairing of charged leptons with neutrino partners. It breaks mirror symmetry in a way that changed our understanding of nature. It connects, through electroweak theory, to the broader gauge structure of the Standard Model. And it may yet be one of the main places where new physics first shows itself clearly. The electron, the muon, the tau, and the neutrinos are not merely sitting in the universe as static entries in a chart. Through the weak interaction, they are engaged in a continuous lawful exchange. Particles become other particles. Energy is redistributed. Identities are matched, mixed, and transformed under strict rules. It is one of the most delicate and important conversations in the cosmos, and without it the lepton family would lose much of the behavior that makes it so revealing. And once that conversation is in place, the natural next step is to widen the view again. Because if leptons are so deeply involved in atomic behavior, radioactive change, stellar fusion, neutrino traffic, and the hidden machinery of particle decay, then they are clearly doing more than simply existing as a tidy family in the Standard Model. They are helping shape the actual world, from the smaller scales of matter to the larger structures lit by stars, which brings us directly to the broader question of how leptons reach outward from the particle table into atoms, stars, and the texture of reality itself. Once the lepton family is seen clearly, it becomes difficult to keep thinking of these particles as tiny, isolated curiosities sitting at the edge of physics. They are not tucked away in some remote theoretical corner. They are built into reality at every scale that matters, from the structure of atoms to the burning of stars. In fact, one of the quiet surprises of the subject is that leptons help shape both the intimate details of ordinary matter and the grander processes that light the universe. They are present in the nearest and most familiar things, and they are present in the deep interiors of cosmic objects we will never touch. They belong to the small scale and the large one at the same time. The most obvious place to begin is with the atom, because here the role of leptons is not subtle at all, even if it often goes underappreciated. The atom is sometimes introduced as though its essence lies in the nucleus, the compact central region containing protons and neutrons, and certainly the nucleus matters. It carries most of the mass. It defines the element. It gives the atom its heavy central identity. But the nucleus alone is not enough to produce the actual behaviour of matter. Without electrons, atoms in the full everyday sense do not exist. Without electrons, there is no chemistry, no molecular bonding, no crystalline structure, no ordinary surfaces, no electrical currents in the familiar form, no life chemistry, no material science, and no stable world of objects interacting in the ways we recognise. That is an extraordinary amount of responsibility for one lepton to carry, and yet the electron manages it without attracting nearly as much public drama as black holes, antimatter, or other flashier members of the physics conversation. It sits in atoms not as a tiny planet orbiting the nucleus in the old textbook picture, but as a quantum participant occupying allowed states. Those states determine how atoms bond, how they absorb and emit light, how they share or exchange electrons, and how they build molecules. The entire periodic table becomes chemically meaningful, because electrons arrange themselves according to quantum rules. Carbon behaves like carbon because of its electron structure. Oxygen behaves like oxygen because of its electron structure. Water, proteins, metals, glass, stone, and skin all depend on the way electrons settle into matter. That is already enough to place leptons at the centre of reality as we experience it, but there is more. The electron does not just participate in atoms, it also helps determine why atoms have size. The nucleus is tiny compared with the overall atom. The surrounding electron structure gives the atom most of its spatial extent. That means the scale of ordinary matter, the reason a table is not as compact as a tiny nuclear pellet, depends heavily on electrons. The world is spacious at the atomic level because electrons occupy quantum states that extend outward from the nucleus. If the electron behaved differently, matter would not simply become slightly altered. It would become a very different kind of thing altogether. This affects the solidity of the world as well. When you touch a wall, a table, a blanket, or your own hand, what you are experiencing is not little hard pieces of matter simply colliding in the old mechanical sense. The electrons in atoms and the quantum rules governing them prevent matter from collapsing into itself or sliding through other matter under ordinary conditions. Electromagnetic repulsion and exclusion effects work together to give the world its stubborn resistance. The lepton here is not just part of the story. It is one of the main reasons the story feels so dependable. Chairs remain chairs. Floors continue their useful habit of being beneath us, rather than letting us drift through them. Everyday reality has a great deal riding on our electron behaviour being exactly what it is. Then there is light. One of the most beautiful things about electrons is that they stand at the centre of our readable universe. When atoms absorb or emit light, electrons are often the reason. They change states. They interact with the electromagnetic field. They create spectral lines, those precise signatures that allow physicists and astronomers to determine what distant matter is made of. So even when a star is far beyond reach, its light tells us about its composition because electrons in atoms are following universal rules. The same electron structure that shapes matter in your body shapes the light emitted by a distant galaxy. That continuity is one of the most elegant features of physics. The laws governing the smallest familiar lepton scale up into our ability to read the cosmos. This means that leptons do more than build the world, they help reveal it. When astronomers study the light from stars, nebulae, galaxies, or interstellar gas, they're often reading the traces of electron transitions. The universe becomes interpretable because electrons leave fingerprints in radiation. Without that, astronomy would be far poorer. We would see light, perhaps, but not understand it in nearly the same detailed way. The lepton is thus not only an architect of matter, but also a translator of distant reality. Electrons also shape technology in ways that are so familiar we almost stop noticing them. Electrical circuits depend on the controlled movement of electrons through materials. Electronics depends on how electrons behave in semiconductors, metals, insulators, and engineered structures. Computing, communication, lighting, sensors, batteries, motors, screens, and countless other technologies all rely on electron behavior being precisely manageable. If the proton gives atoms their identity at the nuclear center, it is the electron that gives civilization much of its practical machinery. One could say, without much exaggeration, that modern society runs on an organized conversation with one member of the Lepton family, and yet the electron is only one lepton. The fuller importance of the family begins to emerge when we turn outward from atoms and look at stars. In stars, leptons enter the story in a different way. Here the electron still matters, because hot ionized matter is full of electrons, and their interactions with radiation are crucial to how energy moves through stellar material. But now the weak interaction and the neutrinos become central as well. In the Sun and in other stars, nuclear fusion does not proceed simply by smashing nuclei together in a blind mechanical way. The process depends on specific reaction chains, and some of the most important steps involve weak interaction processes that produce neutrinos. In that sense, stellar light is tied not only to the electromagnetic life of electrons, but also to the weak interaction life of leptons more broadly. The Sun shines because nuclear fusion in its core converts hydrogen into helium and releases energy. That energy eventually reaches us as sunlight, warming the planet and supporting nearly all surface life directly or indirectly. But buried inside that process are lepton-producing reactions. Neutrinos are emitted from the solar core in enormous numbers. They leave the Sun almost immediately and stream out into space. So while the photons that reach Earth have taken a long and complicated journey through the solar interior, the neutrinos have come more directly. They are messengers from the central furnace itself. This makes leptons part of the actual communication channel between stars and the rest of the universe. There is something rather astonishing about that. A particle family associated in one context with atoms, electricity, and chemistry is in another context carrying news out from the centre of the Sun. The electron gives matter its ordinary form. The neutrino gives stellar interiors a voice. The same family spans both roles, and that makes the leptons feel less like a niche category, and more like a continuous thread running through the whole structure of reality. The role of neutrinos becomes even more dramatic in the life and death of massive stars. When a large star reaches the end of its life and undergoes collapse, neutrinos play a huge role in the event. In a supernova, an enormous burst of neutrinos carries away a tremendous amount of energy. These particles are not decorative byproducts. They are central to the dynamics of the collapse and explosion. The visible spectacle of the supernova is, in some sense, only one surface expression of a much deeper particle event in which neutrinos are major participants. In that moment, the ghostliest members of the Lepton family become some of the most important actors in the cosmos, and these neutrinos do not simply remain theoretical. They have been detected from supernova events, giving direct evidence of processes occurring deep inside dying stars. That is a remarkable achievement, but it also reveals something profound about the structure of reality. There are events in the universe that light alone cannot fully explain. To understand them, we need leptons. We need the neutrino, that nearly invisible particle that slips free from dense matter, where photons struggle. The universe is not only made partly by leptons, it is also, in some of its most extreme moments, understood through them. Leptons also shape the history of the universe at a much earlier stage. In the hot, dense conditions of the early cosmos, leptons were abundant and active. Electrons, neutrinos, and their antiparticles were part of the particle soup through which the young universe evolved. The balance of particles and antiparticles, the rates of interaction, the expansion and cooling of the cosmos, all of this involved leptons in a direct way. Later, as the universe cooled, electrons became part of stable atoms, while neutrinos largely decoupled and continued on through space. So the Lepton family participates both in the early thermal history of the universe and in the later structure of matter and stars. This broad role makes them especially interesting in cosmology. Neutrinos, though tiny in mass, are so abundant that they can influence the evolution of large-scale cosmic structure. Their properties matter to how matter clumped and how the universe expanded and cooled. Electrons matter because once atoms formed, they enabled the universe to become transparent to light in the way that eventually allowed the cosmic microwave background to travel freely. Again and again, when the universe changes phase, from hot plasma to structured matter, from stellar core reactions to explosive collapse, leptons are there. Even on Earth, their influence extends beyond the obvious. Radioactive decay within the planet produces neutrinos. The heat generated by long-lived radioactive elements contributes to geological activity, and weak processes are involved in those decays. Neutrinos stream outward from the Earth just as they stream from the Sun, though with much less drama and brightness attached. We are living not only under a shower of solar neutrinos and cosmic ray products, but also amid a quiet outward flow of particles from the planet itself. The Lepton family is not only in the stars and in atoms, it is moving through the Earth, around it, and out of it. There is also a powerful conceptual point here. Leptons show how the same family of particles can matter in radically different physical contexts. The electron matters because it is charged, light, and stable. It shapes atoms, materials, and chemistry. The neutrino matters because it is neutral, weakly interacting, and capable of carrying information from hidden interiors. The muon and tau matter because they reveal the generational structure of matter and provide sensitive tests of the laws governing the family. The weak interaction links them all, giving the family its dynamism. So when we ask how leptons shape reality, the answer is not one thing. It is many things at once, layered across scale. At the level of life, the electron is indispensable. Biology is chemistry organized in time, and chemistry is electron behavior under highly structured conditions. Bonds form because electrons are shared or exchanged. Molecular geometry arises because electron states and repulsions settle into certain patterns. Metabolism, DNA stability, protein shape, nerve signals, muscle contraction, and the entire molecular infrastructure of living systems all depend on electron physics. A living cell is, among other things, a brilliantly complicated electron environment. So the lepton does not merely shape inert matter. It helps make life possible in the form we know. At the level of materials, electrons distinguish conductors from insulators, metals from semiconductors, transparency from opacity, magnetism from non-magnetism in many contexts, and much else besides. Their collective behavior in solids gives rise to phenomena that are rich enough to support entire fields of study. The same particle that schoolbooks once drew as a tiny orbiting dot becomes, in condensed matter physics, part of a many-body quantum system whose collective effect can be subtle and extraordinary. Again, the electron proves that a lepton can be both elementary and endlessly generative in the structures it helps create. At the level of stars and cosmic events, neutrinos expand the picture. They do not shape chemistry, but they shape our understanding of stellar interiors, supernovae, and the weak processes that govern nuclear change. They remind us that reality is not built only from what interacts strongly with us. Some of the most important cosmic participants are the least visible. That is a useful lesson well beyond neutrino physics. The universe often hides its major mechanisms in places our senses would never have found on their own. There is also a kind of unity in the fact that leptons help connect the local and the cosmic. The electron in an atom and the neutrino from a distant stellar event belong to the same family. The lepton category spans your own body, the circuitry in a machine, the core of the sun, the collapse of a star, and the early universe. That continuity is deeply satisfying because it means the laws are not parochial. They do not stop at the scale of everyday objects or begin only at the scale of astrophysical grandeur. The same family identity persists everywhere. Perhaps that is why leptons, once understood, start to feel less hidden than the title might suggest. At first, they seem like an abstract piece of the Standard Model, a classification term attached to particles most people do not think about. But after a while, the opposite becomes true. It becomes difficult not to see their presence everywhere, in the shape of atoms, in the hardness of solids, in the chemistry of life, in the glow of stars, in the neutrinos crossing the Earth, in the processes that fueled the early universe, in the measurements that let us read distant matter. The family is not remote. It is woven through the whole visible and invisible fabric of the world. And still, after all this, the central question remains richer than a simple list of roles. The electron is not important only because it is useful. The neutrino is not important only because it is elusive. The muon and tau are not important only because they help complete a pattern. What makes the lepton family truly remarkable is that it reveals how reality can be built from a small number of precise identities, whose consequences ramify outward into everything from touch to starlight. This is one of the quiet triumphs of modern physics. The world is complicated, but some of its deepest ingredients are few, exact, and endlessly expressive. So from atoms to stars, leptons shape reality by giving matter its structure, by making chemistry possible, by carrying signals from hidden places, by governing weak processes in stars and decays, by contributing to the history of the cosmos, and by allowing the universe to be read as well as inhabited. The more we look, the less they seem like background particles, and the more they begin to look like one of the main threads holding the story together. And with that wider view in place, only one final step remains in the journey we have been taking all along. If leptons can shape the everyday world, the stellar world, and the invisible traffic of the cosmos, then what does it really mean to say that the hidden particle behind electrons belongs to this family at all? And what kind of answer are we left with when we return at last to the original question of what a lepton really is? After all of this, after the atoms and the stars, after the electrons in matter and the neutrinos in the dark, after the muon and the tau raise their awkward but important question about why the family repeats itself at all, we come back to the simplest version of the problem, and perhaps the hardest one to answer cleanly. What is a lepton really? At first, the answer seems almost too straightforward. A lepton is a fundamental particle of matter that does not feel the strong nuclear force. That is accurate. It is the right answer in the formal sense. It tells you what family the electron belongs to. It tells you why the electron is different from a quark. It tells you why neutrinos can travel through matter so freely, and why the charged leptons are not trapped inside protons and neutrons. It is a good answer. But it is not the whole answer, because a definition and an understanding are not quite the same thing. To understand what a lepton really is, you have to see what that definition is doing. You have to notice that the electron, which seems so familiar at first, only begins to make full sense when it is placed inside this broader family. You have to notice that the family itself is defined not by visual appearance or everyday usefulness, but by the hidden rules of the Standard Model. You have to notice that a lepton is not a tiny object in the old mechanical sense, but a fundamental quantum entity with a precise identity, a fixed set of properties, and a specific place in the architecture of matter. That is already a meaningful shift. The electron is not just the small negative particle from school diagrams. It is the first charged lepton. It carries electric charge. It has spin of the lepton kind. It participates in the weak interaction. It appears to be elementary rather than composite. It is stable because it is the lightest charged member of its family. And from that set of facts, almost everything else about the visible world begins to follow. The atom becomes possible, chemistry becomes possible, materials become possible, biology becomes possible, electronics becomes possible. The familiar world takes shape because the electron is not merely a particle, but a lepton with exactly the right identity. And that identity is not accidental in the shallow sense. It is built into the laws as we currently know them. Every electron in the universe is the same kind of thing, not similar, not approximately alike, but identical in the way fundamental particles are identical. The electron in a distant star and the electron in your own body are not cousins or variants. They are instances of the same basic entity, governed by the same field, the same charge, the same mass, the same spin, the same interactions. That sameness is one of the quiet reasons the universe is stable and intelligible. A lepton is not just matter, it is lawful matter. Once that becomes clear, the rest of the family begins to matter more as well. The muon is not merely an odd, heavier electron. The tau is not a curiosity left over from a cosmic design meeting that got slightly out of hand. The neutrinos are not just small neutral extras floating around the edge of the theory. Together they show that a lepton is not defined by one role in one part of the world. It is defined by a deeper pattern that can be expressed in several forms: charged and neutral, stable and unstable, familiar and elusive, structurally similar yet dramatically different in how they appear in the life of the universe. That is part of what makes the lepton feel like a small mystery rather than a settled piece of cataloguing. We know what its family traits are. We know how those particles behave. We know how they differ from quarks. We know how the electron supports atoms and how neutrinos carry information out of stars. We know that heavier charged leptons decay through the weak interaction. We know that neutrinos oscillate. We know that leptons come in 3 generations. But knowing all that does not fully answer why the pattern is built this way in the first place. The mystery has not vanished. It has simply become more exact. There is something important in that. Science is often imagined as a process of turning mystery into certainty, and sometimes it is. But just as often it turns one vague mystery into a sharper one. Before modern particle physics, the question might have been, what is matter made of? That was broad, necessary and unresolved. Now we have a far more detailed answer. Matter involves quarks and leptons. Electrons are leptons. Neutrinos are leptons. The standard model gives a precise account of their properties and interactions, but the sharper mystery is now why these particular families exist, why there are 3 generations, why the masses take the values they do, why neutrinos are so light, and why the visible world leans so heavily on one stable charged lepton, while the others remain mostly transient. So a lepton is not just a particle in a family, it is also a clue. It is one of the places where nature shows both its clarity and its restraint. Clarity because the family structure is lawful and measurable. Restraint because the deeper reason for the pattern still sits partly beyond reach. If we strip the matter down to its essentials, a lepton is one of the fundamental matter particles that do not carry the strong charge of quarks. That means leptons are not confined into hadrons, they can exist as individual particles. They belong to a branch of matter that remains outside the tight internal world of the nucleus, while still shaping reality at every scale. The electron does this through atoms, chemistry and electricity. The neutrinos do it through stellar processes, weak interactions, and cosmic history. The muon and tau do it by completing the generational structure and giving us heavier versions of the same underlying pattern. The weak force ties the family together through decays, transformations, and neutrino behavior. In that sense, the lepton is not just one thing. It is one kind of thing expressed across several roles. That is why the question of what a lepton really is cannot be answered by saying only small particle. Smallness is not enough. Plenty of fundamental particles are small in any ordinary sense. What matters is the pattern of identity. A lepton has spin of the fermion kind. It belongs to one of the 3 matter generations. It participates in the weak interaction. It may carry electric charge or be neutral. It does not carry the colour charge that would tie it into the strong interaction. That combination of traits gives it a very particular style of existence. If quarks are the densely bound ingredients of nuclear matter, leptons are the freer matter particles that build atoms, cross space, decay through the weak force, and help translate the hidden workings of the universe into something observable. And perhaps that is the most satisfying way to think of the lepton, not as an isolated object but as a category of possibility, a specific way the universe allows matter to exist. The electron is the clearest example, because it is the one the world has made practical use of. It sits in atoms. It arranges itself into quantum states. It shapes molecules and materials. It helps define the size of atoms and the behaviour of solids and liquids. It carries electrical current. It helps determine whether a material is metallic, insulating, reactive, stable, transparent or opaque under certain conditions. It is one of the reasons your body holds together, your thoughts continue, your devices function, and your room remains full of surfaces that behave in familiar ways. If the Lepton family had only one visible public representative, the electron would still be enough to justify its importance. But the family has more to say than that. The neutrino takes the lepton idea in a different direction. Remove electric charge. Leave only the weak interaction and a tiny mass. The result is a particle that passes through stars, planets and bodies almost untouched. A particle that is produced in abundance in the sun and in nuclear processes. A particle that can carry information from environments photons cannot escape easily. A particle that proved our earliest version of the standard model was incomplete, because it turned out to have mass and to oscillate. The neutrino makes the lepton concept bigger than ordinary matter. It shows that leptons are not only what hold the visible world together, but also what move through the invisible traffic of the cosmos. Then the muon and tau arrive and make the whole subject less comfortable in exactly the right way. If the electron and neutrino pair could almost be called necessary for the world as we know it, the heavier generations refuse that easy conclusion. They remind us that nature is not assembled only for the convenience of ordinary matter. The muon and tau exist even though stable chemistry does not require them. They are not mistakes. They are not optional. They are part of the same lawful pattern. Their extra mass and instability make them less visible in daily life but no less real. And because they exist, they force us to ask why the lepton pattern repeats. A lepton, then, is also part of a family structure whose reason we can describe more readily than we can explain. That is not a weakness in the subject. It is one of its strengths. The Lepton family tells us exactly where the frontier still is. We do not live in a universe where everything is unknown, nor do we live in one where everything is already settled. We live in one where the electron is understood well enough to build technologies of extraordinary precision, where neutrinos are studied in giant underground detectors, where the muon is measured closely enough to challenge the standard model at the margins, and where the deepest reason for the family structure is still under investigation. That is a very scientific kind of mystery, not a fog of ignorance, but a sharply outlined gap. There is also something quietly humbling about the scale of the lepton contribution. They are not dramatic in the way planets or black holes are dramatic. They do not arrive as giant visible structures in the sky. They operate below the threshold of ordinary perception. Yet they shape almost everything we do perceive. The visible world is a lepton-rich world because of electrons. The hidden stellar world is a lepton-rich world because of neutrinos. The tests of fundamental physics are a lepton-rich world because of muons and taus. A family that most people never think about turns out to be one of the main ways the universe gets anything done. You might even say that the lepton is one of the forms in which reality becomes practical. Quarks help make the heavy cores of atoms. Leptons make those atoms useful. That is a slight oversimplification, but only slight. Without electrons, nuclei would not give rise to the layered chemistry of the ordinary world. Without neutrinos, the weak processes in stars and supernovae would be a very different affair, and our ability to probe hidden astrophysical interiors would shrink. Without the heavier leptons, the family structure of matter would look simpler. but the universe would lose some of the very clues that currently point us toward what lies beyond our present theories. At the same time, a lepton is not important because it has some human-friendly function. This is worth remembering. The electron does not exist in order that chemistry can happen for our benefit. The neutrino does not exist in order that astrophysicists can struggle nobly with underground detectors. Muons do not exist simply to keep particle physicists employed, though they have certainly been helpful in that regard. Leptons exist because they are part of the fundamental structure of the universe. Their roles follow from their identities, not the other way around. We notice those roles because we live inside the consequences. This is perhaps the deepest shift of all. At the beginning, the electron may have looked like an object inside the atom. Now it looks more like one expression of a deeper type of matter. The word lepton, which may once have sounded like a niche technical term, begins to feel like one of the core categories by which the universe is built. The hidden particle behind the electron was never hidden because it was obscure in importance. It was hidden because familiarity disguised it. We had met the electron long before we understood what sort of thing it really was. And so, when we ask one last time what a lepton really is, the answer is something like this. A lepton is one of the fundamental matter particles through which the universe builds atoms, carries weak interactions, structures chemistry, lights stars, sends neutrinos across space, and reveals both the power and the incompleteness of our current theories. It is not defined by size alone or by one specific job, but by a precise identity in the standard model, an identity that separates it from quarks while linking it to one of the deepest repeated patterns in nature. The electron is the lepton we live with. The neutrino is the lepton that slips past us. The muon and tau are the leptons that remind us there is more to the family than ordinary matter uses. Together they make the lepton not just a category, but a small mystery beneath everything. And now, having come all the way back to the question we began with, it is worth noticing how different it feels. At the start, the electron may have seemed like the main character, and the word lepton like a technical footnote behind it. But by the end, the perspective has quietly reversed. The electron is the familiar face, the lepton is the deeper identity. The ordinary particle from school lessons turns out to be one local example of a broader family that touches almost every layer of reality we have discussed. That, perhaps, is one of the most satisfying things physics can do. It can take something you thought you already knew and reveal that it belongs to a much larger structure without making the original thing any less real. The electron is still the electron. It is still the charged particle in atoms. It is still the carrier of current and the organizer of chemistry. But now it is also a doorway into the deeper order of matter, a familiar presence with a hidden family name. So if you find yourself looking at the ordinary world a little differently after this, that may be the most honest ending we could hope for. The glass on the table, the air in the room, the warmth from a lamp, the distant light of stars, the quiet traffic of neutrinos from the sun, all of it belongs to a universe in which leptons play their roles with exactness and without fanfare. They do not announce themselves. They simply make the world possible, intelligible, and active from the smallest scales to the largest ones we have touched tonight. And wherever you are listening from now, whatever hour it has become in your corner of the world, perhaps that is a pleasant thought to leave resting for a moment. Beneath the surfaces of things, beneath the atoms, beneath the diagrams and the familiar names, there are these small, precise identities, repeating, interacting, shaping matter and starlight alike. The lepton is one of them, quiet, fundamental, and still not fully explained, which is, in its own calm way, a very good reason to keep wondering.